Welcome to the Deep Dive. Today, we're embarking on a really exciting journey into one of the most fundamental, yet I'd say incredibly versatile, transformations in organic chemistry, oxidation.
Yeah, it really is fundamental.
Think of it like the chemical equivalent of a master sculptor. Precisely adding or removing pieces to transform a block of material into something entirely new. That's sort of what we're talking about with oxidation, but at the molecular level.
That's a great analogy. It really captures the transformative power.
It's all about taking a functional group, that specific cluster of atoms within a molecule, and making it more, let's say, oxygen-rich or maybe hydrogen-poor.
Increasing the oxidation state.
Exactly. And this might sound simple, but this seemingly minor adjustment, it just opens up this vast universe of synthetic possibilities. We're talking about everything from, gently converting an alcohol into an aldehyde,
to completely cleaving really tough carbon double bonds, essentially using chemical scissors to cut molecules apart. And our guide for this deep dive today is, well, it's an absolute cornerstone of the field. An extensive chapter on oxidations from Advanced Organic Chemistry, Part B Reactions and Synthesis, the 5th edition.
a classic text.
Oh, absolutely. And this isn't just, a collection of facts. It's a really profound exploration into how these reactions truly operate at the atomic level in the lab. It gives us the why behind the what.
Right. And our mission for you, our listener, is to really extract the most important nuggets of knowledge from this incredibly rich source. We want to give you a shortcut, maybe, to being truly well-informed on this crucial topic.
Complete with some surprising insights, I hope, and definitely practical, real-world takeaways.
Yes, definitely. We'll skip the dry textbook lecture feel and instead dive into, well, hopefully a fascinating conversation, revealing the ingenuity behind these chemical transformations. So are you ready to uncover the power of oxidation?
Absolutely. Let's jump right in. So to start, it's probably important to clarify what oxidation specifically means in the realm of organic chemistry, because it's maybe a bit broader than what you might think of as just adding oxygen.
Right. It's not always just oxygen.
Exactly. Here, it encompasses not just adding oxygen atoms, but also removing hydrogen atoms. Both of those actions effectively increase the oxidation state of carbon atoms within a functional group.
Okay.
And this particular chapter in our source is, well, it's remarkable because it delves into an unusually wide array of mechanisms, much more so than many other chapters. It makes it a particularly rich and fascinating area to explore.
And what's crucial to remember, I think, is that the reactions we'll be discussing aren't just, theoretical concepts or abstract mechanisms floating out there.
No, not at all.
The source material really emphasizes that these reactions are chosen precisely because of their immense utility in organic synthesis.
Right. Practicality is key.
These are the tried and true tools that chemists actively use in labs every single day to build complex molecules, everything from life-saving pharmaceuticals to advanced new materials. They solve real-world problems.
Indeed. And to help us navigate this pretty expansive landscape, we can categorize the transformations into 7 major groups. It helps to organize them by the specific functional group changes they achieve.
Okay, a roadmap. Good.
Yeah, this systematic approach really helps us compare different methods for reaching the same synthetic goal,
Makes sense.
So first, we'll explore the oxidation of alcohols. This can convert a primary alcohol to an aldehyde, or even push it further to a carboxylic acid. And it takes a secondary alcohol cleanly to a ketone.
Okay, alcohols to carbonyls, got it.
Second, we'll look at the precise addition of oxygen at carbon-carbon double bonds. This leads to structures like glycols and epoxides. Think of them as really versatile building blocks.
Right, adding functionality.
Third, there's allylic oxidation. That's where we strategically introduce oxygen at positions right next to a double bond.
The allylic position, okay.
Fourth, we'll tackle the powerful oxidative cleavage of double bonds, basically breaking them into smaller, more manageable pieces.
Chemical scissors again?
Exactly. Fifth, we'll cover the oxidative cleavage of other functional groups, like ketones, which can be used to open rings or break chains. Sixth, we'll examine the direct oxidations of aldehydes and ketones themselves, transforming them into acids or other more oxidized forms.
Okay.
And finally, though it's maybe less common, we'll touch upon oxidation at unfunctionalized CH positions, where it's much harder to introduce oxygen selectively, but still important in some cases.
That sounds like a challenge.
It can be. And to achieve all these transformations, chemists largely rely on 3 main classes of oxidizing agents, or oxidants.
Right.
First, we have the transition metal derivatives, often the real workhorses of organic synthesis.
Okay, metals.
Second, there's a whole fascinating family of reagents based on oxygen itself, along with ozone and various peroxides.
O2, O3.
Yep. And finally, a diverse group of other reagents that offer unique selectivities and applications. So that gives us a clear roadmap for the deep dive ahead.
Excellent. So where do we start? Alcohols.
Let's start right there with a foundational transformation, the oxidation of alcohols. This is all about precisely crafting carbonyl compounds, those molecules containing a carbon-oxygen double bond from alcohols. And our first major class of oxidants here are the transition metals.
And I guess at the very top of that list, we find the chromium reagents.
Absolutely. They are arguably the most widely employed metal oxidants for alcohols, typically derived from chromic trioxide, CrO3, or a dichromate salt, like potassium dichromate, K2Cr2O7.
And what's fascinating here, and maybe often overlooked, is how the specific form of CRBI changes depending on its environment, right?
Yeah.
And how that impacts its reactivity.
That's a really crucial point. It's not just chromium or. For instance, in dilute aqueous solutions, the main species is the monomeric acid chromate ion, HCrO4. But as you increase the concentration, these species start to link up, and the dichromate ion, Cr2O72, dominates.
Dimerization.
Exactly. Then shift to a solvent like acetic acid, and CRVI actually exists as mixed anhydrides of acetic and chromic acid. And if you move into pyridine, a basic solvent, it forms a direct adduct involving a CRN bond.
So the solvent really dictates the species.
Absolutely. While the chromium atom itself always remains in the +6 oxidation state, these distinct molecular forms dictate its precise reactivity. It allows for remarkable selectivity just by choosing the right reagent and conditions. It's like having different keys for different locks, all based on chromium sex.
Okay, so how does the reaction actually happen? What's the mechanism?
Well, when an alcohol meets one of these CRVI reagents, the initial step involves the alcohol coordinating, basically attaching to the chromium atom. Then comes the crucial step, what we call the rate-determining step.
The slow step.
Right. A proton is removed from the carbon atom that's connected to the alcohol group, the alpha carbon, and we have really good evidence for this being the slow step.
Oh yeah, what's that?
It's a classic aha moment for mechanistic chemists, a primary kinetic isotope effect. If you replace that alpha hydrogen with its heavier isotope, deuterium, the reaction slows down significantly.
Because the CD bond is stronger, harder to break.
Exactly. That tells us that the bond to that hydrogen is breaking in the slowest, most crucial step of the entire reaction. It reveals critical details about the mechanism.
That's neat. So CrVI gets reduced.
Yeah.
What happens then?
Right. That initial reduction takes 3R down to Chi, but CrV is highly unstable. It doesn't just sit there. It undergoes further complex transformations, eventually reducing to EQI.
Okay.
But then CrVI is quickly reoxidized by other 3I species that are still around, leading to the formation of CRV. It's this intricate sequence of steps involving CrI, CRV, and RV that ultimately accounts for the overall stoichiometry.
The overall numbers.
Yeah. For every 2 CRV species consumed, 3 alcohol molecules are oxidized. You end up with 3 carbonyl products and 2 CR ions plus some protons. It's a beautifully orchestrated dance of oxidation states.
Wow. Okay, so it's not just a simple one-step reduction.
Not at all. It's quite complex, but leads to a clean overall transformation.
Now, in the practical world, in the lab, chemists have developed a whole range of conditions using these CRVI reagents, like Jones's reagent.
Ah, yes, Jones's reagent. That's an acidic aqueous solution of chromic acid, usually an acetone. It's a real go-to for rapidly oxidizing secondary alcohols directly to ketones with minimal overoxidation.
And you mentioned something about workup.
Yeah, a neat bonus is that the reduced chromium salts, the Cr3 species, often just precipitate out of the acetone solution. That makes the workup, isolating and purifying your product remarkably easy. Just filter it off. Imagine that convenience in a busy lab.
Definitely useful. But what if your molecule is sensitive to acid? Jones is pretty acidic, right?
It is. And for molecules that are a bit more delicate, or if you're concerned about acid sensitivity, the CrO3 pyridine complex, often known as Collins reagent, becomes incredibly valuable.
Okay, so pyridine makes it less acidic.
Exactly. Collins' original procedure involved carefully isolating this complex as a solid and then dissolving it in dichloromethane to get good yields. This method is particularly useful for converting primary alcohols directly into aldehydes without overoxidizing them to carboxylic acids, which can be a real challenge with aqueous chromium reagents.
Right. Stopping at the aldehyde is often tricky.
It is. Later, researchers like Ratcliffe and Rothorst simplified this significantly. They developed an in situ preparation method where you just add CrO3 directly to pyridine and dichloromethane. Much simpler to perform in the lab without sacrificing yield.
Nice. Practical improvements.
Yeah, and they even found that adding things like 4A molecular sieves, these are essentially tiny porous beads that trap water, and a tiny bit of acetic acid could accelerate reactions, especially for sensitive molecules like carbohydrates. Always optimizing.
Then we have PCC, pyridinium chlorochromate.
Right, PCC. That's a solid, usually orange reagent you can make by combining CrO3, hydrochloric acid, and pyridine. It's typically used in nearly stoichiometric amounts, about 1.5 equivalents usually does the trick. It's very effective, especially for converting primary alcohols to aldehydes without pushing them further. Very reliable.
And PDC.
Pyridinium dichromate, PDC. Also a solid, formed from pyridine, CrO3, and water. When you use it in solvents like DMF or dichloromethane, PDC is excellent for oxidizing secondary alcohols to ketones, and it's quite selective for allylic primary alcohols, stopping cleanly at the aldehyde stage.
But it can go further sometimes.
Yes, if you change the conditions, say use DMF, PDC can even take saturated primary alcohols all the way to carboxylic acids if you let it run long enough, or sometimes just to the aldehyde. For example, if you wanted to make decanal, that's CH3, CH2, 8CHO from its alcohol, PDC and dichloromethane can give you a fantastic 98% yield of the aldehyde. That's real synthetic power and control.
Okay, so these chromium regions sound incredibly versatile and powerful, but there's always a but, isn't there?
There usually is in chemistry. While these chromium oxidants are undeniably versatile workhorses, they do come with a significant drawback: their toxicity and environmental hazards. Chromium compounds are known carcinogens.
Right. That's a major issue.
It is, especially when you think about larger scales, like an industry, because these reagents are typically used stoichiometrically, meaning you use roughly the same amount of the oxidant as your starting material, or even in excess.
You generate a lot of waste.
Exactly. You generate substantial amounts of byproducts. And the disposal of these chromium-containing wastes poses an ongoing, costly, and complex challenge for green chemistry and industrial sustainability. It's a constant push for chemists to find greener alternatives.
Which I guess brings us neatly to manganese oxidants. Are they seen as greener options?
They're often seen as more selective and potentially environmentally friendlier options, yes, trying to address some of those chromium concerns. Potassium permanganate, KMNO4, for example, is super powerful. You probably saw it in Gen Chem, that bright purple stuff.
Oh, yeah.
But for alcohols, it often lacks the precision we need. It tends toward over-oxidation and generating side products, which is why it's not always the first choice for delicate selective transformations.
So not always the best tool for the job.
Not for fine synthesis, often. That's precisely where manganese dioxide, MnO2, truly shines. It's particularly useful because of its remarkable selectivity.
Oh, selectivity is key.
Absolutely. Unlike permanganate, MnO2 excels at oxidizing allylic and benzylic alcohols, those with an alcohol group right next to a double bond or an aromatic ring, while often leaving other alcohols untouched.
That's useful.
Very. And its reactivity, interestingly, depends heavily on how it's prepared and dried. Imagine just a slight difference in its preparation can change how effective it is. MnO2 is widely used for very specific transformations, including sensitive conjugated systems where other oxidants might just chew up the molecule.
And the innovation in manganese chemistry doesn't stop there. People are always trying to make things catalytic.
Always. Researchers are constantly looking for ways to make these reactions catalytic and even more selective. For instance, there's a fascinating catalytic system that uses iodosobenzene as the terminal oxidant in combination with a chromium saline complex as the catalyst.
Wait, chromium again? I thought we were talking manganese.
Ah, good catch. That specific iodosobenzene system is chromium catalyzed, but it targets the same type of alcohols, allylic, benzylic, cyclopropyl, that MnO2 is good for, offering a catalytic alternative. Shows how fields overlap.
Okay, got it. So catalytic selectivity for those specific alcohols.
Exactly. Think about it. You can convert benzyl alcohol to benzaldehyde using only a small catalytic amount, just 15 mol% of the key saline complex. That demonstrates the power of catalytic precision.
Okay, back to actual manganese. What about Magtrieve? That sounds like a brand name.
It is. Magtrieve is essentially a specific form of CrO2. Or wait, sorry, chromium dioxide again. My mistake, getting my metals mixed up. Magtrieve is CrO2, not manganese. But it's worth mentioning here because of its unique physical property.
Okay, what's special about it?
This commercially available solid is ferromagnetic. It's attracted to a magnet.
Whoa, really?
Yeah. And this is a game changer for environmental reasons. You can recover it easily with a simple magnet from your reaction mixture and then reactivate it just by exposing it to air at high temperatures.
That's brilliant. Real green chemistry.
It's a wonderful example of practical green chemistry in action. Magtrieve efficiently oxidizes allylic and benzylic alcohols in good yield and can even react with saturated alcohols. For example, oxidizing isobutanol to isobutyraldehyde, Magtrieve can achieve that in a fantastic 90% yield, and you just pull the catalyst out with a magnet afterward.
Okay, so CrO2, but very practical. Now, are there other manganese or related greener options?
Yes, sorry about the detour. Back to potentially greener metals. For instance, potassium ferrate, K2FeO4, which is an iron species, so not manganese, but related high oxidation state metal, when supported on montmorillonite clay, provides clean, high-yielding oxidations specifically for benzylic and allylic alcohols. It's far less reactive with saturated ones, showing valuable selectivity.
Iron, okay. Cheaper than chromium, maybe.
Generally, yes, and less toxic. And for those stubborn saturated secondary alcohols where MnO2 isn't very effective, a catalytic system involving ruthenium II with MnO2 as the stoichiometric oxidant has been developed.
Ah, okay, so MnO2 is still involved, but the ruthenium is doing the catalytic work.
Precisely. Here, ruthenium acts as the primary active oxidant, and an added benzoquinone plays a clever role as an intermediary hydride transfer agent, regenerating the active ruthenium species. It's quite an elegant solution for oxidizing those less reactive saturated secondary alcohols.
Okay, so that covers manganese and some detours. What about ruthenium itself as the primary oxidant, like ruthenium tetroxide?
Right, ruthenium tetroxide, RuO4. Now, this is a truly strong, versatile oxidant, very powerful. It's typically generated in situ, meaning right in the reaction vessel.
You don't store it.
No, it's too reactive and unstable. You generate it as needed using a catalytic amount of a ruthenium source like simple RuCl3, along with a stoichiometric oxidant, such as sodium periodate, NiO4, or sodium hypochlorite, AOCl, bleach, essentially. Acetonitrile is often the solvent of choice because it helps stabilize the ruthenium species, ensuring good yields.
And you said it's powerful.
Incredibly powerful. It's the kind of reagent you pull out when other milder methods have failed. The source actually mentions a specific instance where the oxidation of a complex compound, labeled as 1 to its product 2, was only successfully achieved with RuO4 after numerous other attempts proved fruitless. That really highlights its unique capability.
But power often comes with the downside.
It does. As with many powerful tools, its potency comes with a trade-off. RuO4 readily attacks carbon double bonds, so it can limit its use if you need to keep those intact elsewhere in your molecule.
Okay, so not always compatible with double bonds.
Exactly. However, this very power allows it to achieve some impressive transformations that others can't. It can oxidize primary alcohols all the way to carboxylic acids, not just stopping at aldehydes. It can even convert methyl ethers into methyl esters and benzyl ethers into benzoate esters.
Wow, ether, cleavage, and oxidation.
Yes. Imagine having a mixed ether like CH3CH, CH2, 5CH, OCH2PH, CH3, and being able to selectively convert that benzyl ether portion into a benzoate ester, CH3CH, CH25, O2CPH, CH3, in an excellent 85% yield. That's pretty impressive functional group tolerance and transformation.
Definitely. Any other unique uses?
One truly unique and synthetically valuable application is its ability to convert tetrahydrofuran rings, those common 5-membered cyclic ethers, into gamma-lactones. This is a crucial transformation in many complex multi-step syntheses, for instance, in building intricate natural products where you need that specific lactone structure.
Okay, so RuO4. Powerful, versatile, but watch out for double bonds.
That's the bottom line.
So we've explored the world of metal oxidants. Now let's shift our focus to the category called other oxidants. Where do we start there?
Let's start with the incredibly versatile family of dimethyl sulfoxide, DMSO-based oxidations.
Ah, DMSO. Usually just a solvent, right?
Usually, yes. But here it's the key reagent. The core principle is to use DMSO itself in combination with an electrophilic activator reagent. And there's a whole menu of choices for that activator.
Like what?
You could use dicyclohexylcarbonamide, DCCI, acetic anhydride, trifluoroacetic anhydride, TFAA, oxyl chloride, or even seemingly simple things like sulfur trioxide, SO3, or phosphorus pentoxide, P2O5.
Okay, quite a range. How does DMSO actually do the oxidizing?
The mechanism behind these DMSO oxidations is quite elegant. It begins with the electrophilic activator attacking the oxygen atom of the DMSO molecule.
Makes sense. Oxygen is electron-rich.
Right. This forms a highly reactive sulfoxonium species. Think of it as a sulfur atom that's temporarily carrying a positive charge and is activated. The alcohol then adds to this activated sulfur.
Okay, alcohol attacks the sulfur.
Then, the sulfoxide oxygen, now part of a better leaving group thanks to the activator, departs. This sequence ultimately leads to an intermediate called an alkoxysulfonium phyllide, which is the direct precursor to your carbonyl product.
Moilide.
Yeah. The phyllide then undergoes a clever intermolecular proton transfer and elimination, cleanly yielding the aldehyde or ketone product and regenerating DMSO, although technically it forms dimethyl sulfide, DMS, as the byproduct. The source really dives into this, showing the key intermediates, often labeled A, B, and C, that bridge these steps.
And is there one activator that's most popular?
Yes. Out of this versatile family, the Swern oxidation, which specifically uses oxylyl chloride as the electrophilic activator, has become arguably the most popular.
The Swern. Heard of that one. Why is it so popular?
It's generally fast, efficient, pretty high yielding, and operates under mild, low temperature conditions, usually around -8 degrees Celsius. This makes it great for sensitive substrates. It's a real go-to for many chemists.
And the examples show this versatility.
Absolutely. The source shows the original DCCI procedure, which proved the concept, but then using SO3, or acetic anhydride, really broadened the scope. The acetic anhydride example in particular is noteworthy because it allowed the successful oxidation of an alcohol without disturbing a very sensitive indole ring system elsewhere in the molecule. That's the kind of precision chemists dream of.
That is impressive selectivity.
Yes, and the innovations continued. One example uses a water-soluble carbodiamide as the activator. This is a fantastic practical improvement because the urea byproduct, which can be a pain to remove with DCCI, is water-soluble, making product purification significantly easier.
Ah, smart. Easier cleanup.
Definitely. Then you see examples demonstrating the widespread effectiveness of the classic Swern procedure itself. And for larger scale preparations, there is an example highlighting a 60-gram scale reaction using the incredibly inexpensive P2O5 as the activator. This really showcases how these methods aren't just for academic curiosity, they're truly practical tools for building molecules on a useful scale.
Okay, so DMSO oxidations, especially the Swern, are really important tools. What's next in the other oxidants category?
Next up, we have the Des-Martin reagent, often called Des-Martin periodinane or DMP.
Periodinane.
Sounds like iodine.
Exactly. This is a hypervalent iodine compound, meaning iodine is in an unusually high +5 oxidation state, making it very oxidizing. And it has become an absolutely indispensable tool in the modern organic lab.
Why is it so popular?
You typically use it in inert solvents like chloroform or dichloromethane or acetonitrile, and it rapidly oxidizes primary and secondary alcohols with impressive efficiency and generally very good yields. It's often quite clean.
And what about the byproducts? Iodine compounds can be messy.
That's actually one of its appealing features, especially from a green chemistry perspective. The main byproduct is O-iodose-benzoic acid, or IBX after reduction. This can be easily extracted from the reaction mixture with a base, and even better, it can often be recycled back into the Des-Martin reagent.
Oh, recyclable. That's a big plus. It significantly reduces waste and improves the sustainability of the process compared to, say, chromium reagents. Mechanistically, the alcohol first exchanges with an acetate group on the iodine center, forming an intermediate. Then a base, often the alcohol itself or added pyridine, removes a proton, and the whole thing collapses, cleanly yielding the desired carbonyl compound and the reduced iodine species.
And it works for lots of different alcohols.
Yes, the examples in the source demonstrate its versatility beautifully. It reliably handles a wide range of alcohol structures, making it a powerful general-purpose oxidant for many situations. Mild conditions too, usually room temperature.
Okay, DMP, another great tool. What else?
And then we turn to the fascinating world of oxymonium ions, especially those derived from the stable nitroxide radical TEMPO.
TEMPO, that's 2-man 2 and 6-aldyl-6 tetramethyl piperidine 1 oxyl, right? The stable red radical.
That's the one. TEMPO itself isn't the direct oxidant in these alcohol oxidations, but its corresponding oxymonium ion is the active region in a powerful catalytic cycle.
Ah, catalytic. That's good. How does it work?
Here, a stoichiometric oxidant, meaning you use it in at least equal amounts to your starting alcohol like household bleach, sodium hypochlorite, NaOCl, or N-chlorosicinamide, NCS, is used to oxidize TEMPO to the active oxoammonium species. This species then oxidizes the alcohol, getting reduced back to the hydroxylamine form, which is then reoxidized by the stoichiometric oxidant. This cycle allows you to use just a tiny catalytic amount of the relatively expensive TEMPO.
Okay, so TEMPO is the catalyst, bleach is the bulk oxidant. What does the actual oxidation step look like?
The reaction itself proceeds through an intermediate adduct formed between the alcohol and the active oxoammonium ion. Then there's a base-assisted removal of the alpha proton, leading to the carbonyl product and the reduced TEMPO species, the hydroxylamine.
And what's special about TEMPO oxidations?
What truly sets TEMPO-based oxidations apart is their remarkable selectivity. This is a critical feature in complex synthetic routes.
How so?
They can selectively oxidize primary alcohols to aldehydes while leaving secondary alcohols completely untouched.
Wow, okay, primary versus secondary selectivity, that's huge.
It's incredibly useful when you have multiple alcohol groups in a molecule and only want to functionalize the primary one. You can even push primary alcohols all the way to carboxylic acids under slightly different conditions, often by using sodium chlorite along with the TEMPO bleach system.
So you can choose aldehyde or acid from a primary alcohol?
Often, yes. For instance, you can take a primary alcohol within a carbohydrate, a very sensitive molecule with lots of secondary alcohols, and selectively convert just that primary alcohol to a carboxylic acid, leaving all the secondary alcohols untouched. That's fantastic control.
That really is impressive. Can it be used on a larger scale?
Absolutely. The source highlights an impressive example of converting a primary alcohol to its carboxylic acid with a fantastic 90–95% yield on a 6-kilogram scale. This demonstrates its applicability from the academic lab bench right through to industrial production. It's a very robust and selective method.
Okay, so we've thoroughly covered crafting carbonyls from alcohols, using metals, DMSO, DMP, and TEMPO. Now, what about adding oxygen directly to carbon double bonds, building new blocks with fresh functionality, as you said earlier?
Exactly. Let's start again with transition metal oxidants, focusing first on the dihydroxylation of alkenes. That's the process of creating glycols molecules with 2 hydroxyl groups added across the double bond.
And the classic region for that is potassium permanganate, right? KMNO4.
That certainly can be used, yes.
Yeah.
KMNO4 can convert alkenes to glycols under very carefully controlled cold aqueous conditions, often with a base like an AOH.
How does that work?
The reaction proceeds through a cyclic manganese ester intermediate. This intermediate then gets hydrolyzed, leading to synaddition, meaning both hydroxyl groups end up on the same side or face of the original double bond. This stereospecificity is quite valuable.
But permanganate is pretty strong.
That's the complication. Permanganate is a very powerful oxidant, and it can easily over-oxidize the newly formed glycol, leading to carbon bond cleavage between the 2 hydroxyl groups. It's a delicate balance to stop cleanly at the glycol stage. You have to use it cold and dilute and carefully control the pH.
Right, so side reactions are a risk.
Definitely. You'll sometimes even observe ketols as side products, which are thought to form from further oxidation of that cyclic intermediate before hydrolysis.
Can permanganate oxidize triple bonds too?
It can. It can also oxidize acetylenes molecules with carbon triple bonds all the way to alpha diones, which are compounds with 2 adjacent carbonyl groups. For example, you can take a phenyl-substituted acetylene and convert it to the corresponding diketone in an impressive 81% yield.
Okay. Is there an alternative way to make those diones?
Yes, interestingly, a mixture of sodium periodate and catalytic ruthenium dioxide, OsO₄, can also achieve the same dione transformation from acetylenes, often with similar efficiency. So multiple routes exist.
But for just making the glycol, the diol, what's the best method? Is permanganate the gold standard?
No. When it comes to the real gold standard for syn-dihydroxylation, where you want both hydroxyl groups added cleanly and reliably to the same face of the alkene, osmium tetroxide, OsO₄, reigns supreme.
Osmium tetroxide. Sounds heavy. And probably nasty.
It was heavy, and yes, it's highly toxic and volatile, which are major drawbacks. It's also quite expensive.
So why use it?
Because it is incredibly selective and stereospecific. It forms a cyclic osmate ester intermediate via what's called a 3+2 cycloaddition mechanism. It's a beautifully precise chemical maneuver that almost always delivers the syndiol product with very high fidelity.
Okay, high precision, but toxic and expensive. How did chemists get around that?
Ingeniously through catalytic procedures. This was a huge breakthrough. By using a stoichiometric co-oxidant, an inexpensive and less toxic substance like N-methylmorpholine, an oxide, NMO, or T-butyl hydroperoxide, potassium ferricyanide, or others, you can continuously regenerate the active OsO₄ from the reduced osmium species formed after the diol is released.
So you only need a tiny bit of the osmium.
Exactly. You only need a catalytic amount, maybe 1 to 5 mol%, of the expensive and toxic OsO₄. The co-oxidant does the bulk of the oxidizing work. This makes the reaction much more practical, cost-effective, and safer to run.
And it still gives the same syndiol.
Yes, this catalytic approach ensures that the hydroxyl groups are consistently introduced from the less hindered face of the double bond, and the method even works effectively for alkenes that are typically less reactive towards oxidation. It's a very reliable and widely used method now.
Okay, catalytic OsO₄ for syndiols, but then things got even more sophisticated, right? With chirality.
Oh, yes. Here's where it gets truly transformative. Enantioselective dihydroxylation, famously known as the sharpless asymmetric dihydroxylation, or SAD. This was a monumental breakthrough, winning Barry Sharpless a Nobel Prize for its ability to control chirality, the handedness of molecules.
So making just one mirror image of the diol.
Precisely. It achieves remarkably high enantioselectivity, often close to 100% 8 or enantiomeric excess, in the presence of specific chiral ligands derived from cinchona alkaloids.
Cinchona alkaloids, like quinine, from tonic water.
Exactly. Specifically, derivatives like dihydroquinine, DHQ, and dihydroquinidine, DHQD, are used. These are chiral molecules themselves, derived from natural sources.
And how do they control the reaction?
What's truly ingenious is that dimeric derivatives of these alkaloids, where 2 of these chiral units are linked together by a bridging group like phthalazine, PHAL, or pyrimidine, PYR, are the most effective. They don't just induce high enantioselectivity by creating a chiral pocket around the osmium, they also dramatically accelerate the reaction rate compared to using OsO₄ alone.
Faster and more selective. That's a win-win.
Absolutely. Potassium ferricyanide is typically the stoichiometric co-oxidant used in the SAD reaction. And for practical use, these reagents are even sold commercially as convenient pre-mix formulations called AD mixes. There's AD mix alpha, using a DHQ derivative, and AD mix beta, using a DHQ derivative.
So you just buy the mix.
Pretty much. It contains the osmium catalyst, the chiral ligand, the co-oxidant, and necessary bases. This allows chemists to reliably and predictably obtain either an enantiomer, the left-handed or right-handed version of the desired glycol product, just by choosing the right AD mix. It revolutionized the synthesis of chiral molecules.
Is there a way to predict which enantiomer you'll get?
Yes, that's another beautiful aspect of SAD. There's a fantastic predictive mnemonic model, often depicted visually. It shows how the DHQD-based catalysts, like an AD mix beta, typically guide the osmium tetroxide to approach the alkene from one face, often called the bottom or beta face, while the DHQ-based catalysts, AD mix alpha, guide it from the opposite top or alpha face.
So you look at the alkene structure.
You look at the alkene structure, identify the substituents as large L, medium M, and small s, place it in the mnemonic quadrants, and depending on which AD mix you use, it predicts which face the OsO₄ will attack from, and thus the absolute configuration of the resulting diol. It's like having a molecular blueprint for chirality. It works remarkably well for a wide range of alkenes.
That's incredibly powerful for planning a synthesis. Has computation helped understand why it works so well?
Oh, absolutely. Computational studies, using advanced techniques like hybrid density functional theory, DFT, combined with molecular mechanics, protocols, have really peeled back the layers on the molecular basis for this incredible enantioselectivity.
What did they find?
For instance, a study on styrene using a specific ligand found 2 low-energy transition state structures that both precisely predicted the observed R configuration of the diol product. The remarkable stability and preference for these transition states over others is directly linked to subtle attractive forces like pi stacking and hydrogen bonding, involved in how the alkene substrate binds within the catalyst's chiral pocket.
So it's about fitting perfectly into that chiral environment.
Exactly. Similarly, studies on larger molecules like stilbene confirm that its phenyl groups occupy the same binding sites within the catalyst structure, providing even deeper insights into the precise geometry of these critical transition states where the stereochemistry is determined.
And the synthetic applications must be huge.
Vast and transformative. We see sharpless dihydroxylation used everywhere. to synthesize chiral allylic ethers, complex tertiary allylic alcohols. There's even a neat trick for trans-substituted alkenes, where adding methane sulfonamide cleverly speeds up the hydrolysis of the intermediate osmate ester, sometimes leading directly to useful lactone cyclizations in the same pot.
Wow. Has it been used industrially?
Yes, absolutely. The reaction has been scaled up to kilogram-scale reactions for industrial applications, like the synthesis of intermediates for pharmaceuticals. From selectively hydroxylating just one double bond in complex molecules like geranyl acetate, to providing crucial chiral starting materials for blockbuster drugs like sibuprofen and a vast array of natural products, sharpless dihydroxylation is truly a powerhouse. It's a testament to achieving precisely dialed-in control of molecular handedness.
Amazing. Are there other ligands besides the cinchona alkaloids?
Yes, beyond the cinchona alkaloids, researchers have explored other chiral diamines for use with OsO₄. These likely function by forming hexacoordinate chelates complexes where the diamine binds tightly at 6 points to the osmium center, and these also influence the diastereoselectivity of the reaction.
Diastereoselectivity, meaning controlling relative stereochemistry when there are already chiral centers present.
Exactly. This concept also introduces what chemists call matched and mismatched combinations between the substrate's existing chirality and the chirality of the ligand. The goal is always to find that perfect pairing, the matched case, that delivers both high diastereoselectivity and high enantioselectivity, guiding the reaction down a single highly controlled pathway.
Okay, so that's dihydroxylation. What about making epoxides from alkenes using metals? That's another key transformation.
Right, epoxidation. This leads us to another groundbreaking reaction. Transition metal catalyzed epoxidation of alkenes, especially the famous sharpless asymmetric epoxidation, or SAE. This reaction often employs T-butyl hydroperoxide, TBHP, as the stoichiometric oxidant.
The oxygen source.
Yes, combined with vanadium or, more famously, titanium compounds as catalysts.
What's unique about sharpless epoxidation? Does it also use chiral ligands?
It does, but what's really unique is its substrate focus. It works best on allylic alcohols.
Alcohols again, but allylic ones this time.
Exactly. The hydroxyl group on the allylic alcohol plays a truly crucial dual role. First, it activates the alkene for epoxidation, making it more reactive towards the metal catalyst. Second, and perhaps even more impressively, it directs the stereochemistry of the reaction.
How does it direct?
Well, even before the asymmetric version, using a simple vanadium catalyst like VO-ACAC2 with TBHP converts allylic alcohols to epoxides in good yields. The alcohol coordinates directly to the vanadium via its hydroxyl group. This coordination geometry leads to cis-epoxidation relative to the hydroxyl group in cyclic alcohols. In acyclic systems, it results in diastereoselective syn-alcohol formation, meaning the epoxide forms on the same side as the OH group. This is all consistent with a very specific, optimized 50-degree OCCCC dihedral angle in the transition state.
Okay, so the OH group anchors the molecule to the catalyst and directs the oxygen delivery.
Precisely. But the real game changer, the true revolutionary aspect that also won Sharpless his Nobel, is the sharpless asymmetric epoxidation itself.
How does that achieve asymmetry?
By introducing enantiomerically pure tartrate, esters like diethyl tartrate, DET, or disopyl tartrate, DIPT, to the mixture of T-butyl hydroperoxide and titanium tetrasopropoxide, TiO-IPR4.
Tartrates, like from wine, chiral molecules again.
Exactly, tartaric acid derivatives. These act as chiral ligands for the titanium. Adding either the naturally occurring plus tartrate or the unnatural tartrate allows you to synthesize either an enantiomer of the desired epoxide product with incredibly high enantioselectivity. It gives you complete control over the molecular handedness of the epoxide on demand.
That's incredible control. What's the mechanism look like? How do the tartrates work?
Mechanistically, the allylic alcohol substrate first coordinates to the titanium center, just like with vanadium. Then the tartrate esters are chiral guides, bind to the titanium and create a precise chiral environment around that catalytic center. The active catalyst is actually believed to be a dimeric species, involving two titanium centers bridged by tartrate ligands.
A dimer. Okay, more complex.
Yes. There's a rapid exchange of both the allylic alcohol substrate and the T-butyl hydroperoxide oxidant at the titanium centers during the catalytic cycle. It's a dynamic system.
Have computers helped figure this out?
Immensely. Computational studies, particularly DFT calculations, have provided incredibly detailed, almost microscopic insights into the exact structure of the critical transition state, where the oxygen atom is transferred from the peroxide to the alkene.
What did they find in the transition state?
Figure 12.4 in our source visually walks us through how researchers meticulously built up this transition state model step by step. Key features emerged. For instance, a spiro-peroxide titanium interaction, meaning the atoms involved aren't all in a flat plane, but rather twisted relative to each other. The precise orientation of the peroxide's alkyl group dramatically influences the enantioselectivity, which face of the alkene gets epoxidized.
Interesting. What else?
Also, the CO bond of the allylic alcohol substrate precisely bisects one of the tio bonds in the catalyst, and the tartrate ester groups sit in equatorial positions on the titanium, which surprisingly implies a conformational flip of the five-membered dialite ring must occur to achieve this optimal low-energy arrangement. It's these subtle geometric details that dictate the high selectivity.
Wow, really intricate. Has the practical procedure been improved over time?
Yes, significantly, making it even more robust and user-friendly. Modern procedures typically use truly catalytic amounts of both the titanium isopropoxide and the tartrate ligand, perhaps 5-10 mol%, which saves on expensive reagents.
Good. What else?
The inclusion of molecular sieves is also critical. These tiny porous materials act like sponges, sequestering any trace amounts of water present in the reaction mixture. Water is detrimental to both the reaction rate and, crucially, the enantioselectivity. Sieves ensure a dry, efficient, and highly selective process.
So keep it dry. What about substrates with existing chiral centers? Does that affect things?
Absolutely. Substituted allylic alcohols, those with substituents on the double bond or the alcohol-bearing carbon, show distinct diastereoselectivity in addition to enantioselectivity, meaning the existing chirality in the molecule influences which diastereomer of the epoxide is formed preferentially.
Okay, so mismatched effects again.
Exactly. A DFT study highlighted how the reactant's initial conformation is absolutely critical. Concepts like A1,3 strain, that's steric repulsion between groups in a 1,3,3 relationship along the allylic system, can favor the synepoxide product relative to the largest group when a substituent, R4 in figure 12.6, is larger than hydrogen. If R4 is just hydrogen, the antiproduct is often favored.
So conformation dictates outcome.
To a large extent, yes. Figure 12.7 further illustrates how comparing the energies of different possible transition state geometries reveals why specific pathways are favored, perfectly matching the experimental stereoselectivity observed in the lab for different substrates. It's truly a testament to the predictive power of combining computational modeling with careful experimentation.
And the applications. Where is SAE used?
Scheme 12.9 in the source showcases a wide array of synthetic applications. It includes preparing crucial intermediates for complex molecules like leukotriene C1, which is involved in inflammatory responses. Syntheses of fascinating polyether antibiotics like X206. These examples highlight the broad utility of the reaction and underscore the absolute importance of using molecular sieves to achieve high yields and high enantioselectivity. It's a reaction that has fundamentally changed how chemists approach the synthesis of complex chiral molecules containing epoxides or derived diols.
Okay, so SAE is fantastic for allylic alcohols. But what if your alkene doesn't have that helpful hydroxyl group nearby? Can you still do asymmetric epoxidation?
That's a great question, and yes, there's a powerful method for that too. The Jacobson-Katsuki epoxidation.
Jacobson epoxidation, what does that use?
This powerful method uses chiral manganese complexes. The ligands are typically derived from chiraldiamines and salicylaldehyde derivatives, often called salin ligands. These chiral M-salin complexes act as catalysts.
Okay, chiral manganese this time. What's the oxidant?
Various stoichiometric oxidants can be used, like sodium hypochlorite, NaOCl, metachloroperoxybenzoic acid, MCPBA, or iodosilbenzene, VHIO. The active oxidant generated from the catalyst is believed to be a highly reactive OxO₄ species.
And it works on simple alkenes.
Yes, it's particularly effective for cis-disubstituted and tri-substituted alkenes, often giving very high enantioselectivity.
Is it always stereospecific like the sharpless?
Interestingly, no. These epoxidations are not always perfectly stereospecific with respect to the alkene geometry, meaning if you start with a pure cis-alkene, you might get a small amount of the trans epoxide and vice versa.
Why is that?
This is often attributed to a possible side reaction pathway involving an electron transfer mechanism, potentially forming a radical intermediate which can undergo bond rotation before the epoxide ring closes. This can lead to some scrambling of the original alkene stereochemistry. However, its overall utility is undeniable, especially for unfunctionalized alkenes where SAE isn't applicable.
What are some examples of its use?
The scheme provides diverse examples. Epoxidizing aryl conjugated alkenes, a key step in the synthesis of the side chain of the famous anti-cancer drug Taxol, achieving impressive chemoselectivity for epoxidizing specific double bonds within complex molecules containing multiple alkenes. It's also been crucial in the synthesis of phosphodiesterase inhibitors and precursors to important DNA alkylating anti-tumor agents. It really broadened the scope of asymmetric epoxidation significantly.
Okay, so we've covered the impressive capabilities of transition metal oxidants for both dihydroxylation and epoxidation. But you mentioned earlier there's a whole other world of methods for forming epoxides from alkenes using peroxidic reagents, right? Beyond just the metals.
Absolutely. There are very important non-metal methods, and probably the most general and widely used approach involves peroxycarboxylic acids, often just called peroxy acids or peracids.
Peroxy acids like MCPBA.
Exactly. Metachloroperoxybenzoic acid, MCPBA, is perhaps the most common example, but others like magnesium monoperoxyphthalate, MMPP, or potassium hydrogen peroxysulfate, often known by the trade name oxone, which generates a reactive species in situ, peroxyacetic acid, peroxybenzoic acid itself, and the highly reactive peroxytrifluoroacetic acid are all used. Though one always has to be careful handling peroxides as they can be hazardous.
Right, safety first. How do these work? What's the mechanism?
The mechanism for peroxy acid epoxidation is generally accepted to be a concerted process.
Meaning everything happens at once.
Pretty much. All the bond breaking and forming happens in a single transition state. It consistently gives syn addition, where the oxygen atom is delivered to only one face of the double bond. The proposed transition structure is often described as a butterfly or spiro arrangement, where the peroxy acid arranges itself precisely over the alkene pi system for oxygen transfer.
Is it electrophilic or nucleophilic?
It's definitely an electrophilic process. The peroxy acid acts as the electrophile.
How do we know?
The reactivity trends tell the story. You'll find that adding electron-donating groups, like alkyl groups, to the alkene actually increases the reaction rate. It makes the alkene more electron-rich and more attractive to the electrophilic oxygen.
Okay.
Conversely, adding electron-withdrawing groups to the peroxy acid itself also boosts its reactivity. Think about MCPBA. The chlorine is electron-withdrawing. This makes the peroxy acid oxygen more electron-deficient and more electrophilic. This consistent trend confirms the peroxy acid is seeking out electron-rich double bonds.
So what if your alkene is electron-poor, like conjugated to a carbonyl?
Good question. For those electron-deficient alkenes, you often need a more reactive peroxy acid, like trifluoroperoxyacetic acid, TFPAA. Or you can switch tactics completely and use alkaline solutions of hydrogen peroxide, like H2O2 with NaOH. This operates via a completely different mechanism. A nucleophilic conjugate addition of the hydroperoxide anion, followed by intramolecular epoxide formation.
Ah, different mechanism for electron-poor systems. Have computations backed up the electrophilic picture?
Yes, computational studies generally find that the preferred transition structure involves a hydrogen-bonded peroxy acid positioned roughly perpendicularly to the double bond axis, that spiro or butterfly structure. These studies have calculated activation energies for different substituted ethans. The trends perfectly confirm the electrophilic nature. Adding electron-donating groups like OCH3 or CH3 lowers the activation energy, while electron-withdrawing groups like CN increase it, making the reaction harder, just as you'd expect for an electrophilic attack.
What about stereoselectivity? Where does the oxygen add?
Stereoselectivity is a really big deal here. As a general rule, oxygen addition almost always happens from the less hindered side of the alkene, simply because it's easier for the bulky peroxy acid region to approach that face.
Makes sense. Sterics rule.
For example, norborne, that common bicyclic alkene, gives about a 96.4 ratio of exo to endoepoxide. The oxygen strongly prefers the less crowded exoface, the outside face of the bicyclic system.
But are there exceptions? Can anything override sterics?
Yes, and this is really cool, the hydroxy-directing effect. If you have a hydroxyl group, or sometimes other hydrogen bonding groups like amides, positioned near the alkene, it can literally guide the peroxy acid to its own side of the molecule.
Even if that side is more hindered?
Often, yes. It does this by forming a hydrogen bond with the incoming peroxy acid in the transition state. This hydrogen bonding stabilizes the transition state, creating a low-energy pathway for attack from the syn face, same side as the OH, even if it seems sterically counterintuitive.
That's a powerful directing effect. Has that been studied computationally too?
Extensively. For example, simulations for 2-propanolone allyl alcohol showed a clear preference for transition states where hydrogen bonding occurs between the alcohol OH and the peroxy acid oxygen. These hydrogen-bonded structures were calculated to be 2-3 kilocamole lower in energy, a significant preference. Specifically, the syn-exo structure, where oxygen adds from the same side as the hydroxyl group and from the less hindered exophase relative to the CC bond rotation, was preferred.
Fascinating. What about cyclic systems?
In cyclic systems, subtle torsional effects related to the strain of rotating around single bonds can also play a crucial role. Computational studies on substituted cyclohexanes showed that even small substituents can lead to surprisingly high stereoselectivity. This is often due to maintaining a favorable staggered relationship between the forming CO bond and an adjacent axial allylic hydrogen atom in the transition state, subtly guiding the oxidant.
Okay. Are there alternatives to standard peroxy acids?
Yes, several. You can use a combination of nitriles, like acetonitrile and hydrogen peroxide, to form a peroxymitic acid in situ. This reagent then epoxidizes the alkene, offering an alternative, especially if you want to avoid acidic conditions. And importantly, it can also exhibit the powerful hydroxy-directing effect.
Yeah, interesting. What else?
The reactivity of hydrogen peroxide itself can be significantly enhanced in polyfluorinated alcohols like hexafluoro-2-propanol, H2SIP, or trifluoroethanol, TFE. These solvents are thought to polarize the H2O2 molecule through strong hydrogen bonding and also increase the acidity of the hydroperoxide hydroxyl group, making the H2O2 a much more potent electrophilic oxidant in these specific solvents.
Clever solvent effects. Okay, so peroxy acids and related systems are one major class. What else is there for non-metal epoxidation?
Another incredibly useful class of epoxidizing agents are the dioxirane derivatives, especially dimethyldeoxirane, often abbreviated as DMDO.
DMDO, how's that made? Is it stable?
It's actually quite unstable, so it's typically generated in situ, meaning right in the reaction flask when you need it. The usual method is to react acetone with potassium peroxymonosulfate, which is commercially available as oxone, in a buffered aqueous solution.
Acetone and oxone. Sounds simple.
It is relatively simple to generate. You can then carefully distill the volatile DMDO out, it has a low boiling point, or extract it into an organic solvent like dichloromethane, or even use phase transfer catalysis conditions to generate and use it directly in the organic phase.
How does DMDO compare to peroxy acids?
Mechanistically, it's quite similar. DMDO epoxidations are generally considered to be concerted processes and are definitely electrophilic in character. They react faster with electron-rich alkenes. Computational studies confirm this, showing analogous spirotransition structures and activation energy trends.
Does it show directing effects too, like the hydroxy directing effect?
Yes, DMDO also exhibits cis or syn stereoselectivity directed by nearby hydrogen bonding groups like hydroxyls. However, it's worth noting that sometimes strong steric effects can override this direction, especially if the solvent itself is strongly competing for hydrogen bonding with the directing group. The balance can be subtle.
Any other interesting directing effects with DMDO?
What's really intriguing are potential remote directing effects. There have been reports where groups quite far from the double bond, like urea-NH groups or even sulfonate or mesylate groups, can act as surprisingly strong syn directors for DMDO epoxidation. The current thinking is this might involve attractive electrostatic interactions between slightly positive methylene hydrogens on the substrate and the electron-rich oxygens of the dioxirane ring, guiding the approach even from a distance. Shows how subtle electronic forces can influence reactivity.
Very cool. Are there more reactive versions of dioxiranes?
Yes, researchers are constantly pushing the boundaries. For example, 3-methyl-3, trifluoromethylldioxirane, derived from 1,11,1-trifluoroacetone, is significantly more reactive than DMDO. It's so potent it can oxidize compounds that are typically much less reactive towards epoxidation, like methylcinnamate, an electron-core alkene.
The trifluoromethyl group makes it more electrophilic.
Exactly. Other innovations include using hexafluoroacetone with hydrogen peroxide or using N-diol culpyprid and 4,1 salts as catalytic precursors. The polar effect of their quaternary nitrogen seems to enhance reactivity and stability. There's also 4-thiopyrone SS dioxide, which shows enhanced reactivity, presumably due to the strong dipole of the sulfone group. These are all elegant solutions for tackling challenging epoxidations, though sometimes the origins of their stereoselectivity can be quite complex and debated.
And the ultimate goal here would be asymmetric epoxidation using these, right?
Precisely. And a true crowning achievement in this area has been the development of chiral ketones that can be used to generate chiral dioxirane intermediates in situ for highly enantioselective epoxidation of unfunctionalized alkenes. This is often referred to as the Shi epoxidation, after Professor Yan Shi, who pioneered much of this work.
Chiral ketones generating chiral dioxiranes. Clever. How well does it work?
It can work remarkably well. This allows chemists to create chiral epoxides with high enantiomeric excess, E, from simple alkenes that lack any directing groups, a very difficult task otherwise. We've seen examples in the literature using things like a binup-derived ketone catalyst, or a fructose-derived chiral ketone, or specific alpha-fluoroketones. These can achieve impressive enantiomeric excesses, sometimes over 90% E, even with relatively simple substrates like styrene or various trisubstituted alkenes.
How do these chiral ketones exert control?
They are believed to generate chiral dioxirane intermediates in situ using oxone as the oxidant. Scientists have developed a wide variety of these chiral ketones, from fluorinated tripones to complex carbohydrate-derived structures. These often benefit from subtle polar effects of adjacent oxygens or specific conformations, leading to excellent enantioselectivity. The proposed transition structures for these reactions offer fascinating insights, often showing how the substrate's pi system might preferentially orient itself relative to the chiral backbone of the ketone catalyst, guiding the oxygen delivery with exquisite control.
So it's all about the shape of the catalyst dictating the approach.
Essentially, yes, creating a very specific chiral pocket for the reaction to occur in. And these chiral ketones aren't just for making new epoxides. They can sometimes be used for kinetic resolutions, where they selectively epoxidize one enantiomer from a racemic mixture faster than the other, leaving the unreacted enantiomer enriched. They can also be integrated into catalytic cycles using acetonitrile and hydrogen peroxide, where the dioxirines are potentially generated via intermediate peroximinic acids. It's a very active area of research.
Okay, incredible progress in making epoxides, both with metals and nonmetals, and even achieving high asymmetry. Now, we've learned how to make them, but what do you do with them? What about their subsequent transformations?
That's the crucial next step. These strained, three-membered epoxide rings are incredibly versatile and absolutely crucial synthetic intermediates. Their inherent ring strain makes them reactive.
Reactive towards what?
Primarily towards nucleophiles, those molecules or ions that are attracted to positive charge or electron-deficient centers. This reactivity allows you to precisely introduce new functionality into a molecule by opening the ring. And because the ring opening process is often stereospecific,
Meaning the stereochemistry is controlled.
exactly, you can precisely control and establish the stereochemical relationship between the original epoxide oxygen, which becomes a hydroxyl group, and the newly introduced nucleophile. This allows you to build complex chiral centers with confidence. These multi-step operations, epoxidation followed by controlled ring opening, can accomplish specific oxidative transformations of an alkene that might be incredibly difficult or impossible to achieve cleanly in a single step.
Okay, so let's look at ring opening. What are the main ways? Nucleophilic attacks.
Right, let's look at nucleophilic and solvolytic ring opening first. Under basic or neutral conditions, the incoming nucleophile preferentially attacks the less substituted carbon of the epoxide. Primarily for steric reasons, it's simply more accessible, there's less molecular crowding on that side for the nucleophile to approach. This attack happens from the backside relative to the CO bond being broken.
Like an SN2 reaction.
Exactly like an SN2 reaction. This results in an inversion of configuration at the carbon being attacked and leads to an overall anti-relationship between the original epoxide oxygen, which becomes an SOH, and the newly introduced nucleophile. They end up on opposite sides of the molecule.
Okay, basic conditions. Attack at less substituted carbon, anti-addition. What about acidic conditions?
Acidic conditions, however, are a bit more nuanced and complex. The acid first protonates the epoxide oxygen, making it a better leaving group and activating the carbons towards attack.
Okay, where does the nucleophile attack then?
It depends. If the carbon-oxygen bond is largely intact in the transition state, meaning it hasn't fully broken yet, more SN2-like, then the nucleophile still typically goes to the less substituted position, primarily for steric reasons. But, and this is a critical difference, if the CO bond rupture is more complete in the transition state, leading to significant carbocation-like character developing on the carbon, think more SN1-like, then the nucleophile tends to attack the more substituted position.
Why the more substituted? Isn't that more crowded?
It might be more crowded, but that carbon can better stabilize the developing positive charge through hyperconjugation or resonance. So the electronic factor favoring carbocation stability overrides the steric factor.
Ah, okay, so acid catalysis can change the regioselectivity.
It absolutely can. For example, if you take simple propylene oxide and react it with HBr under acidic conditions, the bromide will predominantly attack the less substituted primary carbon, still mainly SN2-like. But with styrene oxide under acidic conditions, attack occurs almost exclusively at the benzylic position, the carbon next to the phenyl ring, because that position can form a much more stable benzylic carbocation intermediate. Under basic conditions, you'd see attack at both carbons of styrene oxide, but favoring the less hindered primary one.
What about Lewis acids, like BF3 or TCl4?
Lewis acids also catalyze epoxide opening. They coordinate to the epoxide oxygen, activating it. Often, they promote anti-addition of nucleophiles, typically at the less substituted carbon, similar to basic conditions, but often faster or allowing weaker nucleophiles to react. However, with substrates like styrene oxide that can form stable carbocations, Lewis acids can sometimes give mixtures due to that competition between sterics and electronics. The stereochemistry, though, usually shows high inversion at the attacked carbon, suggesting a concerted opening of the Lewis acid-activated epoxide.
Can you use specific nucleophiles for these openings?
Oh, absolutely, a wide variety. Azide ion, N3 for instance, can open epoxides, often catalyzed by lanthanide salts like ytterbium triflate, YbO3, SCF33. This can lead to products like tertiary azides with specific stereochemistry, like diaxial opening of 1-methylcyclohexene epoxide.
What about carbon nucleophiles?
Cyanide ion, CN, is a good one. Under various conditions, like using acetone cyanohydrin with triacetamine, or TMS cyanide with catalytic KCN in a crown ether, or even organoaluminum cyanides. It reacts to form beta-hydroxynitriles, adding both a hydroxyl and a synthetically versatile nitrile group across the original double bond position.
And you mentioned chelation control earlier. How does that apply here?
Right, chelation control is fascinating. Epoxides derived from allylic alcohols often exhibit remarkable regioselectivity when opened with nucleophiles in the presence of certain Lewis acids, like organoaluminum reagents, for example, EET2ALN3 for allylic alcohol. The Lewis acid is thought to coordinate simultaneously to both the epoxide oxygen and the nearby hydroxyl group of the allylic alcohol. This chelation effectively locks the conformation and directs the nucleophile to attack a specific carbon, often overriding the usual steric or electronic preferences.
Wow, using nearby groups to control reactivity remotely.
Exactly. We've seen concrete examples in the literature showing how epoxidation followed by solvolysis reliably leads to anti-stereochemistry. Acid catalysis often dictates impressive regioselectivity, sometimes even involving intriguing intermediates like a phenonium ion abridged carbocation involving a neighboring phenyl ring. Nucleophilic openings consistently show preference for the less hindered carbon, unless electronics dominate under acidic conditions. And metal ion catalysis can enable complex carbon bond-forming reactions, like using organocuprates or Grignard reagents, crucial in challenging syntheses, like that of the natural product of puffalone A.
Okay, so nucleophilic opening is versatile. What about reducing the epoxide, opening it with hydride?
Yes, that's another powerful transformation. Reductive ring opening, where we convert epoxides directly into alcohols using reducing agents. The classic powerful reagent for this is lithium aluminum hydride, LiAlH4.
The workhorse reducer.
Indeed. Being a source of nucleophilic hydride, it follows the rules for basic conditions. The hydride adds preferentially to the less substituted carbon of the epoxide.
Same regioselectivity as other nucleophiles under basic conditions.
Exactly. And for conformationally biased systems like cyclohexane oxides, it typically prefers a diaxial opening pathway, meaning the incoming hydride and the departing oxygen, which becomes axial AxO-H, end up in axial positions on the chair conformer. Though you sometimes have to watch out for a minor competing rearrangement pathway where the epoxide rearranges to cyclohexanone, which then gets reduced, leading to about 10% of the wrong alcohol isomer sometimes.
Are there other hydride reagents used?
Yes, several offer specific advantages or disadvantages. For epoxides that are particularly stubborn or resistant to reduction by LiAlH4, lithium trithylborohydride, like 3BH superhydride, is a much more reactive option. Dissolving metals, like lithium metal in liquid ethylenediamine, can also give good yields, offering a non-hydrate alternative.
What about DIBOL-H, diisobutaluminum hydride?
DIBOL-H is interesting because its regioselectivity can be quite substrate dependent. For a simple terminal epoxide like 1,4,2-epoxyoctane, it exclusively delivers hydride to the primary carbon, giving 2-octanol. But for styrene oxide, where the benzylic position is activated, it gives a mixture, actually favoring hydride delivery to the benzylic secondary position, about 86.14 secondary primary alcohol. This shows how Lewis acidity of the aluminum can start to influence regioselectivity, blurring the lines between purely nucleophilic and electronically influenced attack.
What about borane, BH3. That reduces carbonyls. Does it reduce epoxides?
Diborane BH3 itself is generally not a good reagent for reducing epoxides. It's more electrophilic in nature and tends to give low yields or complex mixtures. If borohydride anion, BH4, is present, reduction can occur, but the major product often results from hydride addition at the more substituted carbon, possibly due to initial Lewis acid coordination of borane influencing the opening. So it's mechanistically different and less synthetically useful than lyolH4 for simple reduction.
So overall, epoxidation followed by lyolH4 reduction is like adding water across a double bond.
Effectively, yes. It serves as a reliable two-step alternative to the direct hydration of an alkene, like oxymercuration, demercuration, or hydroboration oxidation. Specifically, epoxidation lyolH4 reduction achieves the equivalent of Markovnikov hydration. The OH group ends up on the more substituted carbon of the original alkene.
Useful synthetic sequence. Okay, what else can happen to epoxides? Rearrangement.
Yes, indeed. The rearrangement of epoxides to carbonyl compounds is another fascinating and synthetically useful transformation. Here, Lewis acids play a key role again, but instead of promoting nucleophilic attack, they catalyze the isomerization of epoxides into carbonyl compounds, ketones, or aldehydes.
How does that work? Is it like the pinnacle rearrangement?
It's very closely related to the pinnacle rearrangement, which involves the 1-2 migration of a group in a periodinated diol. In epoxide rearrangement, the Lewis acid coordinates to the epoxide oxygen, facilitating CO bond cleavage to generate a carbocation, or carbocation-like species. Then a group, hydrogen, alkyl, or aryl, migrates from an adjacent carbon to the electron-deficient carbon, and the epoxide oxygen becomes the new carbonyl oxygen.
So the product structure depends on which group migrates.
Exactly. The product structure and stereochemistry are determined by the relative migratory aptitude of the substituents and the stereoelectronic requirements of the migration step. Boron trifluoride etherate, BF3.0ET2, is a common and effective reagent for this. Modern catalysts, like bismuth triflate, Bio3SCF3, can even promote this rearrangement catalytically.
Can you control which group migrates?
Sometimes, yes, with clever reagent design. For instance, certain bulky diaryl oxymethylaluminum reagents have been developed that show high selectivity for promoting aldehyde formation by favoring hydride migration over alkyl group migration, even in cases where common Lewis acids like BF3 or SNCl4 would give mixtures. This impressive selectivity is attributed to the steric bulk of the reagent dictating the transition state geometry and favoring the migration of the smaller hydrogen atom. It's a beautiful example of how subtle changes in reagent design can dramatically impact reaction outcome.
What about epoxides derived from functionalized double bonds?
They also undergo interesting rearrangements. For example, vinyl chlorides can be epoxidized to form haloepoxides, which then readily rearrange, usually upon workup or with mild acid, to form alpha haloketone.
Okay. What about enol derivatives?
Enol esters and enol ethers can undergo epoxidation and subsequent rearrangement to form alpha-oxygenated carbonyls. If you epoxidize an enol acetate, for instance, it can rearrange to an alpha-acetoxyketone. The stereochemistry of this rearrangement can be subtly influenced by the choice of Lewis acid or conditions. Progic acids, or TMSOTF, might favor retention of stereochemistry at the migrating carbon, while organoaluminum reagents like alame3 could lead to inversion. Even simple thermal rearrangement can give inversion via a concerted cyclic transition state.
Is there a more reliable way to get alpha-hydroxyketones?
Yes, a more synthetically reliable route often involves the epoxidation of silly-enol ethers. If you treat a silly-enol ether with a peroxy acid like MCPBA, you initially form the epoxide. This then rearranges, often catalyzed by the carboxylic acid byproduct, and after aqueous workup to cleave the silly group, you cleanly get alpha-hydroxyketones, or aldehydes.
Could you use DMDO for this?
Yes, you can also use DMDO to epoxidize silly-enol ethers. Sometimes with DMDO, you can even isolate the intermediate silly-protected epoxide before it rearranges, offering more synthetic options. Alternatively, direct dihydroxylation of the silly-enol ether using catalytic OsO₄ with an amine oxide co-oxidant also works beautifully to give the alpha-hydroxycarbonyl compound after workup.
What about vinyl silanes? Silicon seems to pop up a lot.
Vinyl silanes offer another interesting route for building carbonyl scaffolds. Their epoxides convert cleanly to ketones or aldehydes under mild acidic conditions. The regioselectivity in these rearrangements specifically, which CO bond breaks, is often facilitated by silicon's unique ability to stabilize a positive charge in the beta position, the carbon next to the one bearing the charge, through hyperconjugation. This effect, known as the silicon beta effect, allows vinyl silanes to act as clever carbonyl group equivalents, providing a versatile way to introduce carbonyl functionality where it might otherwise be difficult.
Silicon is quite useful. Okay, one last epoxide reaction you mentioned. Base-catalyzed ring opening to allylic alcohols.
Right. This is a fundamentally different way to open epoxides using very strong non-nucleophilic bases, typically lithium dialkylamides like LDA, lithium disopropylamide, or LTMP, lithium tetramethylpiperidine.
Strong bases. What do they do?
Instead of attacking the carbon, these strong bases selectively remove a proton from a carbon adjacent to the epoxide ring, an alpha proton. This generates a carbanion. The negative charge then pushes out the epoxide oxygen, opening the ring and forming a new double bond, resulting in an allylic alcohol.
So it's an elimination reaction, not substitution.
Exactly, it's an elimination. What's particularly intriguing about the mechanism is the stereochemistry. There's often a selective removal of a proton that is cis to the epoxide ring on the same face. The transition state is thought to involve ion pairing, where the lithium cation coordinates simultaneously to the basic nitrogen and the epoxide oxygen, facilitating a syn elimination, meaning the proton removed and the CO bond broken are on the same side of the developing double bond.
Why use such hindered bases like LDA or LITMP?
The hindered nature of these bases is crucial to minimize unwanted nucleophilic attack by the base itself directly on the epoxide carbons. You want them to act purely as bases, not nucleophiles. Other effective reagents include organoaluminum amides or magnesium amides derived from hindered secondary amines. Their efficacy is believed to stem from both the Lewis acidity of the metal ion activating the epoxide and the hindered nature of the amide preventing nucleophilic side reactions.
Can you achieve this transformation differently?
Yes, you can also use certain electrophilic reagents like trialkyl iodides combined with an organic base like DBU or Hoenig's base to directly form silly ethers of allylic alcohols. Trimethylsilotriflate, TMSOTF, with a very hindered non-nucleophilic base like 2-ferrous-6-aditi-botylpyridine can also achieve this.
So what's the net result of this sequence? Epoxidation, then base-catalyzed elimination.
The overall transformation, combining epoxidation with this specific type of base-catalyzed ring-opening trilamination, is functionally equivalent to performing an allylic oxidation of the original double bond, but with a concomitant migration of that double bond to the adjacent position. It's a very powerful and sometimes counterintuitive synthetic sequence.
Okay, that brings us perfectly to the next major topic. Allylic oxidation itself, targeting that carbon neighboring the double bond directly. You mentioned selectivity is key here.
Absolutely. The challenge for chemists in allylic oxidation is achieving really good selectivity, ensuring the reaction happens cleanly at that allylic position without messing with the double bond itself or oxidizing other sensitive parts of the molecule.
What metals are good for this? Chromium again.
Yes, among the transition metal oxidants, the CrO3 pyridine reagent in methylene chloride, or its analog complex with 3,5,5-dimethylpyrazole, have proven quite satisfactory for directly oxidizing allylic methylenes, CH2 groups, to ketones.
How does that work?
The mechanism is complex and not fully resolved, but evidence often points towards the involvement of allylic radicals or cacations as intermediates. This is consistent with the observation that the double bond often undergoes a shift in position, what we call allylic transposition during the oxidation. It's like the molecule rearranges itself slightly to accommodate the new oxygen atom at the allylic site.
Can other metals do this? Copper, maybe?
Yes. Catalytic copper systems can also achieve allylic oxidation. They typically work through the induced decomposition of peroxyesters, like T-butyl peroxybenzoate, which generate the active copper oxidizing species and potentially radical intermediates.
Can you make it asymmetric?
Yes, and that's where it gets exciting. If you use chiral copper ligands, often based on bis-oxylene or BOX structures, you can achieve enantioselective allylic oxidation, sometimes called the Karash-Sosnovsky reaction. This allows you to precisely control which enantiomer of the allylically oxidized product, often an ester, is formed, as demonstrated by examples like the oxidation of simple alkenes like cyclohexene. That's a significant leap in controlling chirality at the allylic position.
Okay, metals can work. What about non-metal methods for allylic oxidation? You mentioned singlet oxygen earlier.
Yes. The reaction of alkenes with singlet oxygen, often generated through photoxidation. This is a truly powerful and unique method for allylic functionalization.
How does it differ from ground state oxygen?
Singlet oxygen 102 is an electronically excited state of normal triplet oxygen 302. It's much more reactive, particularly towards electron-rich systems like alkenes. For most alkenes that have allylic hydrogens, the predominant reaction with singlet oxygen is the N reaction.
The N reaction.
Yes. It involves the abstraction of an allylic hydrogen atom, a simultaneous shift of the double bond into the allylic position, and formation of a new bond between the carbon that lost the hydrogen and one of the oxygen atoms. This yields an allylic hydroperoxide, H group, as the initial product.
Hydroperoxide. Are those stable?
Not always. They are typically unstable and often reduced in situ, using something like sodium sulfite or triphenylphosphine, to the corresponding, more stable allylic alcohol. So the net transformation is the introduction of a hydroxyl group at the allylic position, accompanied by transposition, migration of the double bond. It's a very clever way to functionalize the allylic position while moving the double bond.
Okay, how do you actually get singlet oxygen in the lab? You mentioned photooxidation.
Right. The most common and practical way is through dye-sensitized photoexcitation. You dissolve the alkene in a photosensitizer dye, like rose bengal, methylene blue, or a porphyrin, in a suitable solvent, bubble oxygen gas through it, and then irradiate the solution with visible light, often using a simple lamp. The dye absorbs the light, gets excited, transfers this energy to ground state triplet oxygen, converting it into the reactive singlet state right there in the solution.
Are there non-photochemical ways?
Yes, several. You can generate it chemically, for instance, by reacting hydrogen peroxide with sodium hypochlorite, basically H2O2 and bleach. It's a classic demonstration. There are also methods involving the thermal decomposition of unstable precursors like endoperoxides or phosphite ozonides. Unstable trialkylsilly hydrotrioxides have also been used as sources.
Does the solvent matter much?
Profoundly. The lifetime of singlet oxygen varies dramatically depending on the solvent. It can range from a relatively long 700 microseconds in carbon tetrachloride or furans down to a mere 2 microseconds in water, or about 20-30 microseconds in common organic solvents like methanol or dichloromethane.
Wow, huge difference. Why?
The solvent molecules can physically quench the excited singlet state back down to the ground triplet state through vibrational energy transfer. Periodic solvents with OH or NH bonds are particularly efficient quenchers. This huge difference in lifetime drastically impacts the efficiency of the oxidation. A longer lifetime means the singlet oxygen has more time to find and react with the alkene before it decays. Choosing the right solvent is critical.
How does alkene structure affect reactivity?
Reactivity generally increases with alpha substitution on the alkene. More substituted alkenes react faster. This indicates that the reaction involves an electrophilic attack. The somewhat electron-deficient singlet oxygen is seeking out the electron-rich pi system of the alkene. Interestingly, simple terminal alkenes with the double bond at the very end of a chain are often relatively unreactive towards the alkene reaction. The reaction also has a very low activation enthalpy, but a highly negative entropy of activation, suggesting a highly ordered transition state.
What about stereoselectivity? Where does the hydroperoxide group end up?
Steric effects usually dominate the facial selectivity. The hydroperoxy group is typically introduced on the less hindered face of the double bond system.
Okay. Now, you mentioned the mechanism was debated. Concerted, ania, or an intermediate?
Yes. There was a long-standing debate. Is it a fully concerted process where the H abstraction and CO bond formation happen simultaneously in one step? Or does it involve a short-lived intermediate, possibly a parapoxide, a 3-membered ring with 2 oxygens and 1 carbon, or a diradical? Most experimental and computational evidence now strongly supports a mechanism involving a parapoxide-like intermediate or transition state.
Carboxylic. Okay. What about regioselectivity if there are multiple different allylic hydrogens?
That's where it gets really interesting and sometimes counterintuitive. For triasubstituted alkenes especially, there's often a preference for abstracting a hydrogen from the more substituted end of the double bond system. And a particularly useful rule of thumb is the cis effect.
The cis effect. What's that?
For alkenes like cis-2-butene or Z-alkenes in general, there's often a preference for removing a hydrogen from the allylic position on the more sterically congested side of the double bond.
Wait, the more crowded side. That seems wrong.
It does seem counterintuitive sterically, but it's a well-documented phenomenon. It's thought to be due to a more favorable transition state geometry, where the incoming singlet oxygen can interact favorably, perhaps through weak hydrogen bonding or orbital interactions, with hydrogens on both allylic carbons on that cis's face simultaneously, leading to a lower energy pathway. However, this effect isn't universal and doesn't seem to apply strongly to alkenes with very bulky T-butyl substituents.
Are there other directing effects from functional groups?
Yes. Polar functional groups like carbonyls, cyano groups, sulfoxides, or even silly and stanyl groups can strongly direct the proton removal to occur from a geminal methyl group. meaning a methyl group attached to the same carbon that bears the allelic hydrogen being removed, and hydroxyl and amino groups, similar to what we saw with peroxy acid epoxidation, often favor stereoselectivity. The hydroperoxide group adds to the same face as the OH or NH group, suggesting transition stabilization through hydrogen bonding is again playing a role.
This sounds really complex. Is there any way to change or control these selectivities?
One really cutting-edge approach is using zeolite cavities. You absorb the photosensitizer dye and the alkene reactant inside the tiny molecular-sized pores or channels of a zeolite material. The singlet oxygen reaction then literally occurs inside this confined space.
Confined reaction. Does that change things?
Dramatically. The confinement actually changes the observed regiochemistry and stereoselectivity. For instance, the cis effect is often reduced or even reversed inside the zeolite, and there can be a stronger preference for abstracting hydrogens from methyl groups. This is likely due to enforced conformational changes of the alkene within the cavity and specific electrostatic interactions with the zeolite framework itself. Scientists have even found that using fluorocarbon solvents can further improve the efficiency and selectivity of these intrazeolite oxidations, opening new avenues for highly controlled synthesis.
Zeolites. Fascinating. Have computers helped understand the pure epoxide mechanism better?
Yes, computational studies have been crucial. Calculations of the potential energy surface suggest that the reaction likely proceeds through a peroxide structure which exists at or very near a saddle point on the energy surface. This means there might be little or no actual energy barrier to the subsequent hydrogen abstraction step once the peroxide is formed, suggesting a very rapid, almost downhill process from there. Further detailed computational models of these peroxide transition states consistently account for stereochemical outcomes like the cis effect, finding that the peroxide structure required for abstracting a cis hydrogen is simply lower in energy, leading to that observed selectivity.
Okay. What are some concrete examples of using singlet oxygen?
Scheme 12.17 in the source demonstrates the versatility. Examples show singlet oxygen being generated from simple chemical reactions, H2O2 NaOCl, alongside the more common photosensitized procedures. One particularly impressive example involved a large-scale 25-gram reaction where the intermediate allelic hydroperoxide wasn't isolated, but was cleverly dehydrated in situ to form an alkene conjugated to a ketone using an improved, more stable photosensitizer. This really shows the practical scalability and utility of these methods for building useful functional groups.
Does singlet oxygen only do the ND reaction?
No, it can undergo other types of reactions depending on the substrate. For instance, with electron-rich alkenes like vinyl ethers or enamines, it can undergo a 2+2 cycloaddition to form unstable 1-2 dioxetane intermediates. These dioxetanes often fragment, leading to oxidative cleavage of the original double bond. This can be synthetically useful, like cleaving an amino ketones cleanly to beta-diketones. And of course, for conjugated anes, singlet oxygen readily undergoes 4+2 diols-alder type cycloadditions, forming stable cyclic endoperoxides, so it's quite versatile.
Okay, singlet oxygen is a powerful tool. What's our final other oxidant for allylic transformations?
Our final specific reagent here is selenium dioxide, SeO2.
Selenium. Sounds toxic again.
Selenium compounds do need to be handled carefully, yes. But SeO2 is a synthetically useful reagent specifically for allylic oxidation. Depending on the exact conditions and workup, it can yield allylic alcohols, alpha, beta unsaturated carbonyl compounds, eniones or enols, or allylic esters.
How does CO2 work? What's its mechanism?
The mechanism of CO2 oxidation is generally accepted to be a fascinating three-step sequence involving selenium in the +4 oxidation state.
Okay, what are the steps?
First, there's an electrophilic INI reaction between the alkene and CO2, or more accurately, selenous acid, H2SeO3, formed in the presence of water. This forms a new carbon-selenium bond at the terminus of the original double bond.
Step 1, Inzillian reaction.
Second, this intermediate undergoes a rapid 2.3 sigmatropic rearrangement. This is a concerted rearrangement where electrons shift around a 5-atom system. It cleverly restores the double bond to its original location while effectively moving the selenium-oxygen connection to the allylic carbon.
Ah, a sigmatropic shift. Clever way to functionalize the allylic position.
Very clever. And third, there's the solvolysis or hydrolysis of the resulting selenium ester, a COC linkage, which cleaves the carbon-selenium bond and releases the functionalized organic product, usually the allylic alcohol or carbonyl compound, regenerating a reduced form of selenium.
Can you control whether you get the alcohol or the carbonyl?
To some extent, yes. If you specifically want the allylic alcohol, you often run the reaction in acetic acid as a co-solvent. This tends to form allylic acetate esters via solvolysis, which can then be easily hydrolyzed to the desired alcohol. Otherwise, under different conditions, further oxidation of the intermediate allylic alcohol to the corresponding conjugated carbonyl, enone or eno, is a common and sometimes desired outcome.
Have mechanistic studies confirmed this picture?
Yes, isotope labeling studies and computational work beautifully support this N2,3 rearrangement mechanism. For instance, B3LIYP631G computations strongly support a concerted N-type mechanism for the initial step, and the calculated activation energies align well with experimental isotope effects, providing strong evidence for the proposed pathway.
What about regioselectivity? Where does it oxidize if the alkene isn't symmetrical?
Good question. For trisubstituted alkenes, the oxidation typically occurs at the more substituted end of the double bond during the initial N-reaction step. This again highlights the electrophilic nature of the attack. The selenium reagent is drawn to the more electron-rich, more substituted vinyl position.
Can you use SCO2 catalytically?
Yes, that's a significant practical improvement. You can use catalytic amounts, say 1.52 mol% of SCO2, along with a stoichiometric amount of a co-oxidant like T-butyl hydroperoxide, TBHP. This combination is effective for converting alkenes primarily to allylic alcohols, even working for some poorly reactive alkenes.
And what about stereoselectivity? Does it favor E or Z products?
Here's a particularly useful stereochemical outcome. When SO2 oxidation is applied to trisubstituted gemdimethyl alkenes, those having two methyl groups on one end of the double bond, it predominantly yields the E-lilic alcohol or the E-unsaturated aldehyde.
The E isomer.
Yeah.
Trans double bond. Why?
This preference is explained by looking at the geometry of the five-membered transition state for that crucial 2-per-3 sigmatropic rearrangement step. In that transition state, the larger alkyl group attached to the double bond preferentially adopts a pseudoequatorial conformation to minimize steric strain. This conformational preference directly translates into the formation of the E geometry in the product double bond. It's a nice example of stereo control through transition state conformation.
Is there any other way to use selenium for allylic oxidation?
Yes, there's an alternative indirect oxidative process. This involves first adding an electrophilic aryl selenoyl halide, like FeHSEK or Feseber, across the alkene double bond. This is followed by solvolysis, often with water or alcohol, to introduce an OH or OR group, and then an oxidative elimination of the selenium moiety. This elimination typically proceeds via oxidation of the selenium to a selenoxide intermediate, which then undergoes a spontaneous syn-elimination to form a new double bond, yielding an allylic alcohol or ether.
So additional elimination sequence.
Exactly. An experimentally simpler version uses a mixture of diphenyl diselenide, FeSef, and phenylselenic acid, FeHSCO2H, which generates the active electrophilic selenium species in situ. In this process, the hydroxyl group generally ends up at the more substituted end of the original carbon-carbon double bond, following Markovnikov's rule in the initial addition step. It's another versatile and controlled way to introduce oxygen functionality at the allylic position, often with complementary regioselectivity to CO2.
Okay, selenium chemistry offers some unique tools. Now let's shift gears again to one of the most drastic, but also synthetically very useful, oxidative transformations. The oxidative cleavage of carbon-carbon double bonds, using those chemical scissors again.
Precisely. This is all about making precision cuts, breaking a larger molecule, specifically at the site of a sequence double bond, into two smaller, often difunctionalized fragments, which usually contain carbonyl groups.
How is this usually done? Does it go through the diol we talked about earlier?
Often, yes. Many methods effectively proceed via glycols as intermediates. The double bond is first dihydroxylated, and then that resulting glycol is subsequently cleaved oxidatively.
Can you do it one step?
Yes, and sometimes under remarkably mild conditions. A very popular and efficient method is the Lemieux-Johnson oxidation. This uses sodium periodate, AiO4, as the stoichiometric oxidant, and just a catalytic amount of osmium tetroxide, OsO₄.
Osmium again, but catalytic. How does periodate help?
It's a beautiful catalytic cycle. The catalytic OsO₄ performs the initial dihydroxylation of the alkene, forming the glycol as an osmate ester intermediate. Then the sodium periodate serves two roles. First, it cleaves the glycol-CC bond, releasing the two carbonyl fragments. Second, and crucially, it simultaneously reoxidizes the reduced osmium species back to the active OsO₄ state, allowing the cycle to continue. It's very elegant and efficient, giving you direct cleavage to aldehydes or ketones using only a tiny amount of osmium.
Are there other similar systems? Permanganate?
Yes, you can achieve a similar one-pot cleavage using periodate ion plus a catalytic amount of potassium permanganate. The permanganate forms the glycol, and the periodate cleaves it and regenerates the permanganate. Ruthenium tetroxide, RuO4, again generated catalytically from RuCl3 with sodium periodate as the stoichiometric oxidant, is also highly effective for oxidative cleavage, often taking aldehydes further to carboxylic acids. In all these systems, the expensive or toxic metal is used only catalytically because the periodate co-oxidant does the heavy lifting of both cleavage and catalyst regeneration.
So these periodate methods are quite general for cleavage.
Very general and widely used. We've seen numerous examples, including powerful applications in multistep syntheses, where extraneous carbon atoms need to be precisely removed from a molecular skeleton, or where specific aldehyde or ketone groups need to be introduced for further subsequent transformations like Wittig reactions or aldol condensations.
What about using strong oxidants like chromium or permanganate directly, without periodate? Can they cleave double bonds?
Yes, strong oxidants like chromium reagents, like chromic acid, or stoichiometric potassium permanganate under vigorous conditions, hot concentrated, can also cleave double bonds.
Is that useful?
It can be, particularly for converting cyclic alkenes directly into open-chained dicarboxylic acids by breaking open the ring. For example, oxidizing cyclohexene with hot KMnO4 gives adipic acid.
What's the mechanism thought to be? Still via the glycol.
It's generally thought to involve initial attack on the double bond, possibly forming an epoxide or a glycol monoester intermediate after solvolysis or addition, which is then further oxidized, leading to cleavage.
Are there downsides to using these strong direct conditions?
Yes. The main complications are often competing side reactions. You can get allylic attack occurring alongside or instead of cleavage, which can lead to the loss of carbon atoms and shorter chain products than expected. You can also get unwanted skeletal rearrangements like pinnacle-type rearrangements of epoxide or glycol intermediates, especially under acidic conditions, which can result in rearranged product structures you didn't intend. These complexities underscore why choosing the right oxidant and conditions is so critical for achieving the desired clean cleavage. The periodate methods are generally much milder and more selective.
Okay, so periodate methods are usually preferred. But when people think of double bond cleavage, the absolute classic go-to method that everyone learns is ozonolysis, right?
Absolutely. Reaction of alkenes with ozone, O3, is arguably the most general and selective method for cleaving carbon double bonds. It's a cornerstone reaction in organic chemistry.
Ozone, that's O3. How does it work? What's the mechanism?
The mechanism, famously elucidated by Rudolf Kriege and often called the Kriege mechanism, is beautifully understood thanks to decades of research using low-temperature spectroscopic techniques like NMR and IR and isotopic labeling studies. It's a multi-step process.
Okay, what's the first step?
It begins with a rapid 1-3 dipolar cycle addition of the ozone molecule across the alkene double bond. Ozone acts as a 1-4-3 dipole here. This forms a highly unstable 5-membered ring intermediate called a 1-2-3 trioxylane, often referred to as the primary ozonide or molazonide.
Unstable. So what happens next?
It rapidly fragments. The primary ozonide literally breaks apart in a retro 1-3 dipolar cycle addition. It cleaves 2 CO bonds and the CC bond, splitting into 2 smaller pieces. A standard carbonyl compound, an aldehyde or ketone, and a highly reactive species called a carbonyl oxide, sometimes known as the Kriege intermediate.
Carbonyl oxide, what does that do?
It's also a 1-4-3 dipole, and it quickly recombines with the other carbonyl compound fragment that was formed, but in a different orientation. They undergo another 1-4-3 dipolar cycle addition to form a different, more stable 5-membered ring containing 2 carbons and 3 oxygens, the 1-terphenylamine-4-trioxylane. This is what chemists usually just call the ozonide.
Ah, okay, so primary ozonide forms, fragments, then recombines to the final ozonide.
Exactly. All these steps are generally exothermic, meaning they release energy. Ozone itself is a very electrophilic 1-4-3 dipole, meaning it readily attacks electron-rich double bonds. The initial cycle addition is usually very fast, even at low temperatures like -78 degrees C, which is where ozonolysis is typically performed.
So you form the ozonide. Is that the final product? How do you get the aldehydes or ketones?
No, the ozonide itself is usually not isolated. It's an intermediate that still contains peroxide linkages and can be explosive if isolated and warmed. The real trick, and where a lot of the synthetic control comes in ozonolysis, is in the workup conditions used after the ozone reaction is complete. This step is absolutely crucial for determining the final products.
Okay, different workups, give different products, like what?
Well, if you just did a simple hydrolytic workup, adding water, you would get your desired carbonyl compounds, aldehydes, ketones, but the process would also generate hydrogen peroxide, H2O2, as a byproduct from the breakdown of the ozonide. And H2O2 can then cause secondary oxidation, especially oxidizing any aldehydes formed further to carboxylic acids. Not ideal if you want just the aldehydes.
Right, unwanted overoxidation.
Yeah.
So how do you prevent that?
That's precisely why a reductive workup is by far the most common and generally useful approach. After forming the ozonide at low temperature, you add a mild reducing agent before warming the reaction up. This reducing agent breaks the peroxidic bonds in the ozonide in a controlled manner, directly yielding the desired aldehyde and/or ketone products without generating H2O2.
What reducing agents are used?
Dimethyl sulfide, DMS-CH3-SCH3, is probably the most popular choice. It's efficient, reduces the ozonide cleanly to the carbonyls, and gets oxidized to dimethyl sulfoxide, DMSO, both of which are relatively easy to remove during purification. Zinc dust and acetic acid is another classic reductive workup. Trivalent phosphorus compounds like triphenylphosphine, PPH3, are also effective, getting oxidized to triphenylphosphine oxide. Sodium sulfite or sodium bisulfite can also be used.
So reductive workup gives aldehydes and ketones. What if you want carboxylic acids from the aldehydes?
Then you use an oxidative workup. You intentionally allow hydrogen peroxide to be formed or even add extra H2O2 during the decomposition of the ozonide. This ensures that any aldehyde fragments initially formed are immediately oxidized further to the corresponding carboxylic acids. Ketone fragments, being harder to oxidize, generally remain as ketones.
Okay, reductive for aldehydes, ketones, oxidative for carboxylic acids from aldehydes. Can you get alcohols directly?
Yes. If your goal is to obtain the alcohols corresponding to the carbonyl cleavage products, you can perform the ozonolysis and then, instead of adding DMS or zinc, add a strong reducing agent like sodium borohydride, NaBH4, or even LyLH4 directly to the cold reaction mixture containing the ozonide. This reduces the ozonide and any initially formed carbonyls all the way down to the alcohols in one pot. Very convenient sometimes.
Clever. Are there other tricks? Intercepting intermediates?
Yes, there are even clever ways to intercept those reactive intermediates formed during the fragmentation recombination process, allowing for more control or different products.
Like what?
If you perform the ozonolysis in an alcoholic solvent like methanol, the alcohol can actually trap that highly reactive carbonyl oxide intermediate as it forms, converting it into an alpha hydroperoxy ether. This prevents the normal ozonide from efficiently reforming. Then, if you treat that hydroperoxy ether intermediate with a reducing agent like dimethyl sulfide, you can reduce the hydroperoxide part, releasing the second carbonyl compound. This can sometimes be useful for selectively modifying one fragment differently from the other.
Interesting. Any other trapping methods?
Yes, ozonolysis carried out in methanol containing a strong base like NaOH or sodium methoxide, often with dichloromethane as a co-solvent, can directly lead to esters as the final products instead of aldehydes or acids.
Esters directly.
It's thought that under these conditions, both the carbonyl oxide intermediate and any aldehyde fragments formed are trapped by methanol and or methoxide, and then further oxidized by ozone or other species present, leading directly to methyl esters. For example, a cyclic alkene, like cycloctene, can be converted directly to dimethyl octenidiolate, the dimethyl ester of the C8 dicarboxylic acid, under these precise conditions.
Wow, directly to esters. That's efficient.
It can be. And in some more advanced applications, chemists have even added highly reactive external carbonyl compounds like methyl pyruvate to the ozonolysis reaction mixture, specifically to trap the carbonyl oxide component generated from the substrate alkene. This allows you to essentially swap out one of the carbonyl fragments, converting the original double bond carbons into completely different functionalities, leading to highly complex and tailored molecular structures. Ozonolysis is really a remarkably versatile reaction depending on how you run it and work it up.
It really sounds like it. Okay, we've covered cleavage of double bonds. What about oxidizing ketones and aldehydes themselves? Modifying existing carbonyl structures. Let's start again with transition metal oxidants.
Right. While carbonyls are generally more stable to oxidation than alcohols or alkenes, they can undergo certain oxidative transformations. Ketones, for example, can undergo what we call oxidative cleavage, particularly when treated with strong oxidants like CRRA or MnCV reagents, often under harsh conditions like strong acid or heat.
Cleaving ketones, why would you do that?
It's sometimes synthetically useful, especially for synthesizing difunctional molecules by precisely breaking open cyclic ketones to form open-chain dicarboxylic acids or related
Why
compounds.
does this ketone cleavage work? What's the mechanism?
The mechanism is believed to generally involve oxidation occurring at the alpha carbon, next to the carbonyl, likely via the enol intermediate of the ketone. The enol is more electron-rich and susceptible to oxidation. Studies on specific ketones, like benzyl phenylketone using CRV, showed not only oxidative cleavage products like benzoic acid, but also alpha-oxidation products like benzyl, the alpha-diketone, and even some dimeric products, which strongly suggest the potential involvement of radical intermediates, perhaps arising from reactions of intermediate CRIV or CRV species.
So it might not be a simple single pathway.
Likely not. Interestingly, both the diketone and the cleavage products observed from benzyl phenylketone oxidation were shown to potentially arise from an initial alpha-hydroxyketone intermediate, in that case benzoin, which is then further oxidized. For simple cyclic ketones like cyclohexanone, the oxidation to adipic acid is thought to proceed through intermediates like 2-hydroxycyclohexanone and 1-Bacr-2-cyclohexanedione, which are then cleaved.
Can you start from an alcohol and go straight to the cleaved product?
Yes, since alcohols readily oxidize to ketones under these strong oxidizing conditions, if you use vigorous enough conditions, hot acid, strong oxidant, alcohols can conveniently serve as the starting materials for these more aggressive oxidative cleavages of the intermediate ketone.
Okay, so ketone cleavage is possible, but maybe harsh. What about oxidizing aldehydes? They seem easier to oxidize.
Yes, aldehydes are generally much easier to oxidize than ketones, typically being converted to carboxylic acids. Both MnCA and CRI, chromic acid, can achieve this readily.
What's the mechanism for aldehyde oxidation with CRI, similar to alcohols?
It's thought to be quite similar. The aldehyde likely first forms a hydrate in aqueous acid, adds water across the CO. This hydrate then reacts with the CR species to form a chromate ester. This ester then decomposes in a rate-determining step involving removal of the hydrogen directly attached to the original aldehyde carbon, releasing the carboxylic acid and reduced chromium. Very analogous to the alcohol oxidation mechanism.
What are some good practical conditions for oxidizing aldehydes to acids?
For practical applications, effective conditions include using potassium permanganate, KMNO4, in a mixture of T-butanol and water buffered with NaOH2PO4. Or, perhaps more conveniently and commonly used today, is buffered sodium chlorite, NaClO2. Sodium chloride is often used with a chlorine scavenger like 2-methyl-2-butene to prevent side reactions. It's quite selective for aldehydes.
Any green chemistry aspects here?
Yes, for those focused on greener methods, both KMNO4 and NaClO2 can be used effectively when immobilized on solid supports like silica gel or ion exchange resins. This makes the product work up much, much easier after the reaction. You simply filter off the solid supported reagent. Very practical.
What about older methods? Anything classic?
For a truly classic touch, silver oxide, Ag2O, often generated in situ from silver nitrate and base Tollens reagent conditions, essentially, has long been used for cleanly oxidizing aldehydes to carboxylic acids. It often gives excellent yields, for instance, converting a hydroxy-substituted benzaldehyde to its corresponding carboxylic acid in 83–95% yield. Still a reliable method sometimes.
Okay, aldehydes to acids is straightforward. Can you oxidize aldehydes to anything else? Like esters?
Yes, there's a fascinating transformation for converting aldehydes directly to esters using manganese dioxide, MnO2, in the presence of sodium cyanide, NaCN, in an alcoholic solvent like methanol.
MnO2, cyanide, and alcohol. How does that give an ester?
The mechanism proposed involves the alcohol first adding to the aldehyde to form a hemiacetal. This is then oxidized by MnO2, possibly via a radical pathway involving cyanide to generate an intermediate acyl cyanide. This highly reactive psilocyanide is then immediately solvolized by the alcohol solvent to yield the desired ester product. It's a very clever one-pot transformation from aldehyde directly to ester.
Very neat. Okay, what about oxidizing ketones at the alpha position?
Right.
Adding oxygen right next door.
Right, alpha oxidation of ketones. One reagent historically used for this is lead tetraacetate, PbOAC4. It can react with ketones, presumably via their enol form, to introduce an acetoxy group, OAC, at the alpha position, forming alpha acetoxy ketones.
Lead doesn't sound great. How well does it work?
Yeah, lead reagents are generally avoided now due to toxicity. Also, the yields for direct ketone alpha acetosylation with PbOAC4 are often low or moderate, and for unsymmetrical ketones where there are two different alpha positions, you frequently get mixtures of regiosomers, which is problematic for synthesis. Boron trifluoride, BF3, can catalyze the reaction, likely by promoting the formation of the enol intermediate, making it more reactive towards the lead reagent.
Are there better ways? Starting from enol derivatives.
Yes, starting from preformed enol derivatives is usually much more reliable. For example, if you react enol ethers with PBOAC4, you can get alpha-methoxyketones. And if you start with sileenol ethers, PBOAC4 still yields alpha-cetoxyketones, often more cleanly than starting from the ketone itself.
Can you get alpha-hydroxyketones this way?
Yes, using silicon ethers is a great starting point for alpha-hydroxyketones too. We mentioned earlier that catalytic osmium tetroxide, OsO₄, with an amino oxide co-oxidant like NMO, will directly convert sileenol ethers into alpha-hydroxyketones after aqueous workup. That's a very reliable method.
Okay. Can you oxidize the enolate directly, the anion?
Absolutely. Other procedures for alpha hydroxylation rely on generating the enolate anion first, using a strong base like LDA or KHMDS, and then trapping that nucleophilic enolate with a suitable electrophilic oxygen source.
What oxygen sources work for enolates?
Several have been developed. A molybdenum peroxide complex, specifically MoFi-pyridine HMPA, often called MOOP, is effective. It can oxidize enolates of a wide range of carbonyl compounds, aldehydes, ketones, esters, lactones, to their corresponding alpha-hydroxy compounds, often in good yields. For example, the source mentions an 85% yield for hydroxylating a lactone enolate.
Molybdenum. Okay. Anything else?
A very important and widely used class of reagents for enolate hydroxylation are N-sulfonyloxyuridines. These are stable three-membered ring compounds containing an NO bond.
Oxyuridines. How do they react with enolates?
They act as electrophilic oxygen transfer agents. The enolate nucleophilically attacks the oxygen atom of the oxyuridine ring, opening it up. Subsequent collapse of an intermediate delivers the oxygen to the alpha carbon, forming the alpha-hydroxycarbonyl compound and releasing a sulfonamide byproduct.
Do they offer any selectivity?
Yes, they often show good stereoselectivity. Hydroxylation typically occurs preferentially from the less hindered face of the enolate. This is particularly useful when dealing with chiral substrates, like ketone enolates derived from chiral auxiliaries, for example, acyloxyzolidinones, where high diastereoselectivity can often be achieved.
Can you get enantioselectivity using these?
Yes, that's another major advantage. Chemists have developed chiral N-sulfonyloxyuridine reagents, like those derived from camphor. When these chiral reagents are used to oxidize prochiral enolates, they can achieve high levels of enantioselectivity, producing predominantly one enantiomer of the alpha-hydroxyketone product. This is a very powerful tool for asymmetric synthesis.
Okay, lots of ways to oxidize near the carbonyl. Now let's shift to a really classic reaction involving ketones and peroxides. The Baeyer-Villiger oxidation, what's that all about?
Ah, the Baeyer-Villiger.
Right.
This is a fascinating and very useful rearrangement reaction where an oxygen atom is effectively inserted into one of the carbon-carbon bonds adjacent to a ketone-carbonyl group. It converts ketones into esters, or cyclic ketones into lactones, cyclic esters.
It's inserting an oxygen atom. How does that happen? Peroxide's involved again.
Yes, the reaction typically uses peroxy compounds, most commonly peroxy acids like MCPBA, peracidic acid, or trifluoroperoxyacetic acid, or sometimes hydrogen peroxide under specific conditions, usually with acid catalysts.
What's the mechanism?
It's a well-studied mechanism. First, the peroxy acid protonates the ketone carbonyl, activating it. Then the peroxy acid adds nucleophilically to the carbonyl carbon, forming a tetrahedral intermediate, often called the Krieg intermediate, different from the ozonolysis one.
Okay, addition first, then what?
Then comes the crucial, usually rate-determining rearrangement step. The peroxide OO bond breaks heterolytically, and simultaneously, one of the groups originally attached to the carbonyl carbon migrates with its pair of electrons over to the adjacent oxygen atom. This migration happens concurrently with the departure of the carboxylate leaving group. The result is the formation of an ester, or lactone, where oxygen has been inserted between the carbonyl carbon and the migrated group.
Migration. Does any group migrate? Or is there a preference?
Ah, that's the key. There is a very well-established migratory aptitude, a preference for which group moves. This is a cornerstone rule of the Baeyer-Villiger reaction.
Okay, what's the order?
The general order of migratory preference is roughly tertiary alkyl group, secondary alkyl group, a benzyl, a phenyl, primary alkyl group, cyclopropyl methyl group. Hydrogen also migrates very readily if you start with an aldehyde.
So the most substituted alkyl group usually moves.
Generally, yes, or groups that can stabilize positive charge well, like phenol. For example, if you have a methyl ketone, RCOCH3, the larger R group will almost always migrate, yielding an acetate ester, ROCOCH3. This migratory preference is largely controlled by the migrating group's ability to bear a partial positive charge in the transition state of the migration step. More substituted groups are better at this. Electron-donating substituents on a phenyl ring enhance its migratory aptitude, while electron-withdrawing groups decrease it. Silyl substituents also significantly enhance migratory aptitude.
What about the stereochemistry of the migrating group? Is it retained?
Yes, absolutely. As is typical for migrations to electron-deficient centers, like in many carbocation rearrangements, the configuration of the migrating group is fully retained during the Baeyer-Villiger oxidation. If you start with a chiral group, it migrates without inversion or racemization. This is very important synthetically.
Are there other factors besides electronics that influence migration? Sterics, conformation?
Yes, particularly in rigid cyclic systems, stereoelectronic factors can become very important. There's often a strong preference for the group that is anti-paraplanar, meaning oriented 180 degrees opposite to the breaking OO peroxide bond in the transition state to migrate. This conformational requirement can sometimes even outweigh the normal electronic migratory preference if the molecule is locked in a specific shape.
Can you give an example?
A fascinating example involves cis and trans isomers of 2-fluoro-4-T-butyl cyclohexanone. They show contrasting regioselectivity in the Baeyer-Villiger. In the cis isomer, the non-fluorinated carbon migrates, while in the trans isomer, the fluorine-substituted carbon migrates preferentially. This is explained by subtle dipole repulsions disfavoring the transition state for migration of the CF bond when it's cis to the bulky T-butyl group and the reacting center.
Wow, subtle effects making a big difference.
Exactly. Another example is 2-trifluoromethyl cyclohexanone. Here, the unsubstituted methylene group migrates preferentially over the trifluoromethyl substituted methane carbon. This is due to the strong electron-withdrawing inductive effect of the CF3 group, which strongly deactivates the adjacent carbon for migration. It doesn't want to bear positive charge. Computational energy profiles further illuminate this, showing the reaction proceeds through a minor conformation of the initial adduct, where the bulky CF3 group is axial, allowing the preferred anti-paraplanar alignment for methylene migration. It really highlights the interplay of conformation and electronics.
This reaction sounds powerful. Where has it been really important synthetically?
The Baeyer-Villiger reaction has found immense application, especially in the synthesis of complex natural products. A landmark example is its use in the synthesis of prostaglandins, a class of powerful biological signaling molecules.
How is it used for prostaglandins?
The famous Corey-lactone, a crucial intermediate in many prostaglandin syntheses, was originally prepared by E.J. Corey using a Baeyer-Villiger oxidation of a specifically designed bicyclo 2.2.1 heptan 2,1 derivative, a Nor-Bornemann derivative. This single reaction cleverly established both the required oxidation pattern and the crucial trans-relative stereochemistry of two substituents needed for the prostaglandin framework. It was a brilliant strategic use of the reaction.
Still used today.
Oh, yes. More recently, in the industrial synthesis of travoprost, an anti-glaucoma medication which is a prostaglandin analog, a similar bicyclo 2.2.1 heptan 2,1 derivative is converted to the required lactone using the Baeyer-Villiger reaction. Even though the reported yield was only 40% with 3.1 regioselectivity, the unwanted regiosomer could be removed, making it a viable and efficient route on scale.
Any other examples?
Another impressive example involves converting 2-vinyl-3-silyloxybicyclo 3.2.0 heptan 6,1s, which have a strained 4-membered ring fused to a 5-membered ring, into important prostanoid precursor lactones using just hydrogen peroxide and trifluoroethanol. Here, the inherent strain of the cyclobutanone ring strongly favors the Baeyer-Villiger insertion into the 4-membered ring over competing epoxidation of the vinyl group, leading to excellent yield, 98% of the desired lactone. It shows how you can use strain to drive selectivity.
Baeyer-Villiger, a classic with enduring power. Okay, finally, let's quickly revisit the oxidation of enolates and enolate equivalents using oxygen or peroxides, focusing on alpha functionalization.
Right. We touched on MOOP and oxyzirridines earlier for alpha hydroxylation, but you can also use molecular oxygen, O2 itself, or hydrogen peroxide under the right conditions.
Oxygen itself, don't ketones just sit there in air?
Ketones themselves are generally unreactive towards ground-state triplet oxygen, but their enolate anions, generated with strong bases, are much more electron-rich and nucleophilic, making them susceptible to reaction with O2.
So base plus air.
Essentially, yes. The combination of oxygen, often simply bubbled through the solution or using air, and a strong base, like potassium T-butoxide, KHMDS, or LDA, can introduce an oxygen function directly at these carbanionic alpha sites.
What's the initial product?
Alpha hydroperoxides, OH, are believed to be the initial products. If a reducing agent like DMSO, or more commonly trialkyl phosphite, like POET3, is added during the workup or included in the reaction, the intermediate hydroperoxide is immediately reduced, and the corresponding alpha hydroxy alcohol is isolated directly. This process works effectively for ketones, esters, and lactones.
What's the mechanism? Is it straightforward?
The mechanism is generally considered to be a radical chain autoxidation process, initiated perhaps by trace metal impurities or single electron transfer. The propagation steps likely involve reaction of the enolate carbanion with oxygen to form a peroxy radical, which then abstracts a hydrogen or undergoes electron transfer. However, arguments for non-chain reaction pathways have also been advanced. It can be mechanistically complex. Hydrogen peroxide, H2O2, under basic conditions, can also be used directly as the oxidant to form the alpha-hydroxy compound, possibly proceeding through a nucleophilic attack of hydroperoxide ion on the carbonyl, followed by rearrangement, or via the enolate.
What about starting from silly-enol ethers again? Can they be alpha-hydroxylated with peroxides?
Yes, silly-enol ethers provide a cleaner entry point sometimes. Reacting a silly-enol ether with M-chlorperoxybenzoic acid, MCPBA, leads to alpha-hydroxy ketones after aqueous workup to remove the silly group. If the workup includes acylation, like adding acetic anhydride, alpha-isoxy ketones can be obtained directly.
How does MCPBA react with a silly-enol ether? Epoxidation.
It's believed to proceed by initial epoxidation of the electron-rich enol ether double bond by MCPBA. This forms a transient silylated epoxide, which then undergoes ring opening and rearrangement, possibly involving migration of the Sily's group, ultimately leading to the alpha-oxygenated carbonyl product after hydrolysis.
And we already covered N-sulfonyloxyzirridines as excellent reagents for oxidizing enolates to alpha-hydroxy ketones, often with good stereo control.
Exactly. They are very useful complementary reagents, reacting via nucleophilic attack of the enolate on the oxyziridine oxygen, and offering opportunities for both diastereoselective and enantioselective alpha-hydroxylation.
Wow. We've truly navigated an incredible landscape of oxidations in organic chemistry today. It's mind-boggling how many ways chemists have devised to control the introduction of oxygen or the cleavage of bonds.
It really is. From the classic, sometimes brute force, workhorse chromium reagents that defined an era of synthesis, to the incredibly elegant and subtle catalytic asymmetric methods like sharpless dihydroxylation and epoxidation that absolutely revolutionized our ability to make chiral molecules selectively. We've seen how chemists can precisely control oxygen insertion and carbon bond cleavage. It's a testament to decades of ingenuity.
Absolutely. And we've explored some fascinating and often quite complex mechanisms along the way, from thinking about those precise spiro transition states in epoxidations to the elusive peroxide intermediate and singlet oxygen reactions, and even the intricate dance of oxidation states in chromium reactions. And we saw how powerful computational chemistry has become in helping us visualize and understand these processes at an almost atomic level, giving us that molecular microscope view.
That understanding is key to developing even better methods.
And crucially, we highlighted the powerful synthetic applications throughout. These aren't just reactions confined to textbooks or academic journals. These are the essential tools that chemists use every day to build complex natural products, to create life-saving pharmaceuticals like prostaglandins or Taxol, and even just to enable the precise transformation of a simple alcohol into a ketone with incredibly high selectivity and yield. The ability to rearrange matter at such a fundamental level with such control is, well, it's pretty amazing.
It really underpins so much of modern chemistry and materials science. So what does this all mean for you, our listener? Perhaps consider this provocative thought. The ability to precisely add or remove oxygen, or even to break carbon bonds with such exquisite control, is a profound testament to chemistry's power to engineer the very building blocks of matter. Looking forward, what new structures, what new functions, what new solutions to global challenges in medicine, energy, or materials will these finely tuned oxidative reactions enable in the next decade of discovery? The possibilities seem truly limitless.
That's a great point to ponder. This deep dive really only scratched the surface of this vast and ever-evolving field of oxidation chemistry. But hopefully, it's given you a solid foundation and, more importantly, really sparked your curiosity to learn more. Keep exploring, keep questioning.
Thank you for joining us on this deep dive into organic oxidations, brought to you by the Last Minute Lecture family. We hope you feel more informed and maybe even inspired by the intricate, beautiful dance of atoms and electrons that shapes our chemical world.